Yeah. And recording started.
All right, welcome back, everyone. We're gonna get started with our first talk of the afternoon. So we have Rodolfo Angeloni here to talk about GEMINI. So it's a virtual talk, so go ahead, take it away.
Thank you everyone, and good afternoon again. I'm gonna talk about SCORPIO, the next facility instrument for the Gemini South telescope that I'm pretty sure will be of interest for the NGN community. So the first public images from the Rubin that came online just a few weeks ago have confirmed, I think beyond any reasonable doubt, that the future has arrived. The future is now, is here. We already live in the epoch of big surveys, panchromatic observations, multi-messenger astrophysics, and with Rubin already online and the next generation of extremely large telescopes whose first light is coming closer and closer, I think it has become clear that in order to keep enlarging the horizon of our understanding of the universe, we have to make the best use of each single photons, each and every single photon. I will say each photon matters. So it's basically in this perspective, in this philosophy, in this spirit, if you want, the International Gemini Observatory with its twin 8.1 meter telescopes, one located in Hawaii, the other one in Chile, is currently developing SCORPIO, the next generation facility instrument for the Gemini South telescope. SCORPIO is envisioned to be a major player in the fast follow-up of time domain events discovered by Rubin, but not only Rubin, also the other present and future surveys. And in doing so, it will be basically fulfilling one of the strategic goals of GEMA, an NSF-funded program whose main goal has been to foster the leadership role of the observatory in the era of the multi-messenger astronomy, focusing in particular on two large areas, high spatial resolution, adaptive optics basically, and time domain astrophysics. So what is SCORPIO? SCORPIO, in short, the spectrograph and camera for observation of rapid phenomena in the infrared and the optical, is an 8-channel instrument that can take simultaneous images from the G to the K band, even at high time resolution, as well as medium resolution spectra over basically the same wavelength range, all within a 3 arc-minute field of view and with a pixel scale of 0.18 arc-second per pixel. Quite naturally, beyond such an ambitious and complex project, there is a large team, actually so large that it doesn't even completely fit into the slide, made of people with an impressive variety of backgrounds and expertise. And I'm glad to be representing all the group now today here. So SCORPIO was intrinsically designed to be highly versatile. So it's not surprising in the end it can tackle a wide range of research fields and topics. Everyone will find his own and beloved science case in the virtually infinite list of things that SCORPIO will be able to do. And I'm pretty sure you will also find thousands of different ways in which SCORPIO can help you answer scientific questions in the dynamic AGN universe that you are mostly interested in. So how does it look like? Here it is. To the best of my knowledge, SCORPIO is going to be the largest and heaviest instrument ever mounted at the Gemini South telescopes, with almost 2 tons. And in this representation, in this drawing, it appears mounted on the lateral port of the telescope, connected interface through it via the ISS. It doesn't stand for International Space Station, but it's the instrument support structure. If we start disassembling it, we could already start to recognize its main structural components. So for example, here we have the connecting plates between the real instrument and the telescope itself through the ISS. On the side, we have the cool electronic boxes housing the computers and everything that is directly connected to the low-level instrument software and the control of the environmental parameters. And then here we have trapped within this frame the cryostat, that's basically the SCORPIO near-infrared core. If we manage to imagine to peel back another layer, then we get a glimpse, a more direct glimpse of its highly complex optomechanical layout that is packed, is full of mirrors, beam splitters, and dichroics. Without entering into the details, just to give you an idea of the intricate path the light beam coming from the telescopes takes before reaching the 8 detectors at the end of the optical path, just consider that SCORPIO counts with more than 130 single optical elements. It's really a complex instrument, and from this complexity also comes its power. So in this short video, they say that one image is more than 1,000 words. I hope that one video is more than 1,000 images. You will see this video recorded at the Fractal Labs in Spain, where the instrument is currently being assembled. And here, in the first shot, you see the focal plane mechanism and its multi-slit element that is mounted on this second rail. So you will see that the instrument is gradually taking shape and form. But what will SCORPIO actually be capable of? What kind of performance should we expect from it? So in this plot, what I'm showing you is the simulated imaging and spectroscopic throughput, both with and without the atmospheric dispersion corrector. That it's going to be deployable. And basically, if you want to use it or not, at the price of a slight decrease in throughput, depends on the need of each observing program. SCORPIO has been naturally designed to take full advantage of the superb atmospheric conditions, sync conditions at Cerro Pachón. And I think there is no need of reminding you that actually Gemini South and Rubin are just a few hundred meters away on the top of Cerro Pachón, one beautiful mountains on the Chilean Andes. So if we want to get into a bit more into the details, this table summarizes the expected performance in imaging mode, again under average weather conditions. And I think it's not surprising to realize, since both Gemini South and Rubin are 8-meter class telescopes, that the performance are practically comparable in terms, for example, of limiting magnitude, considering 10 seconds short exposures. When using spectroscopic mode, SCORPIO lets the user choose between 7 different slits, 7 different slit width, all 3 arc minutes long, so encompassing the entire field of view. And in this table, you can actually see the corresponding resolving power for each one. While in this other table, that is similar to the one I've just shown for the imaging mode, you can have an idea of the expected performance in spectroscopy. We mentioned at the beginning that SCORPIO is envisioned to play a leading role in the fast follow-up of time domain events. And as a matter of fact, this need has driven 2 main designs for the instrument. A high-speed imaging mode, about which I won't tell you much unless you explicitly ask for after during the questions, and a slit viewing camera. The slit viewing camera basically allows us to acquire a spectroscopic target without the need of deploying the imaging mode, thus eliminating on one cut all the normally associated overheads related to the reconfiguration of the instruments back to the imaging mode, spectroscopic mode, sorry. Those of you who have used GMOS, for example, in the past, that are GMOS users, know exactly what I'm referring to. So just to give you an example, a first taste, let's say, of what an AGN observation might look like with SCORPIO, together with my friend and colleague Swayan, who should be somewhere there in the remote space, we imagine SCORPIO observing a 20 magnitude candidate AGN, again under average sync conditions. So in the Gemini jargon, CC50 photometric condition, IQ 70, let's say 0.6, 0.7 arcsecond sync, relatively dark time, and at an air mass of 1.5. We ran some simulations. We've tried out different detector readout strategies and exposure times, and in the end came up with this kind of, let's say, first order estimate that you have, again, to take as an estimates, but I think they can give you an idea of what we might expect in the near future. So imagine for a moment that you are the PI of a disruptive rapid TO proposal at Gemini South, and for whatever reason, you know better than I do, decide to trigger an observation. By using the SBC for the acquisition, so cutting down again the acquisition overhead, we can have your candidate IGN into the slit in about 6 minutes from the time we receive the trigger and we start slewing the telescope to the position. Adopting the standard ABBA nodding strategy, typical of near-infrared spectroscopy, we could then deliver a spectrum with a signal to noise of around 10 in K in about, even slightly more probably, in about 1800 seconds on target, meaning that the total execution time for the whole observing sequence will be about or slightly less than 40 minutes. And I think this is not bad, right? But I feel that the most important question now is when all this is supposed to happen, right? So SCORPIO is currently into its assembly, integration, and verification phase, while the corresponding commissioning and science verification phase is expected to occur at Cerro Pachon in 2027, early 2028. So with this rapid summary that I'm afraid it will leave you with more questions than answers, I can just invite you to stay tuned. Feel free, of course, to contact me anytime if you have any questions or curiosity about SCORPIO. And by concluding this talk, I would like to thank you all for the attention, even if I don't see you directly, and in particular for the kind of opportunity that I've been given to talk to you about this wonderful project during your annual science collaboration meeting. Thank you again, and good luck for what is left.
Great. So we have time for some questions. Does anyone have any questions? Want to start off? Okay. All right. So I guess how accurate do you think that start timeline is? And what do you foresee with it lining up for, kind of the Rubin data releases?
Well, there have been, as it's usual, unfortunately, in these big projects, some delays, but I think the timeline I've just shown is quite confident because we are already in an advanced stage of the project. So the instrument is actually taking place. Some critical tests are already going on. So a cooling test for the cryostat and all the on a parallel line, all the low-level software and even data reduction pipeline is being developed, actively developed. So to wrap up, I think that these dates are quite okay, realistic.
And so I guess there's a question on Zoom. Swami, you want to unmute and ask?
Yeah, not a question, but I just wanted to add for the community at large, SCORPIO is part of GEMINI, which also provides an open sky program, in principle allowing any scientist anywhere in the world to apply for time with GEMINI under this program. So effectively, this is an instrument for every one of you. So we look forward to listening and getting more questions, even from all of the communities apart from the partner countries. So just wanted to add what Rodolfo already said on that point. Thanks.
Thank you,
Sounds
Sylvia. Yeah.
Yeah, sounds like it's maybe something that we can think about in the follow-up group, right? So. Okay, oh yeah, go ahead.
So what kind of proposal would it be? Is there such a thing as a TO proposal, or will it be a new class proposals once LSST is up? How do you ask for time? The best way to ask for time in the system?
Well, Gemini has a very different and very good strategy for requesting observing time. We have regular semestral proposals. We have, of course, the DDT, directory discretionary time, but we also have the fast turnaround type of proposals where you basically can apply every month if you have some self-sustained, relatively short idea that you want to verify. You can basically apply at the end of every month. The next month is designed for the proposal evaluation, and all the proposals that get approved through this fast turnaround basically get in the queue and potentially on Sky at the beginning of the other month. So let's assume that now we are in July, you decide to apply at the July deadline. August will be devoted for the proposal checks, and if approved, you will get theoretically, potentially, your observations executed already in September. And fast turnaround proposals usually live in the queue for up to 3 months. So September, October, November would be the time in which you most likely get your observations executed. And within these different ways, of course, you have the different flavors of target of opportunity, the standard one, the rapid TO, or the normal one.
Is it possible to propose like we want to have 20 TOs, but we'll tell you the month before which one they are? We may have a watch list in this group, and we won't know until like a month before which the best targets to look at. Is that proposal kind of possible?
Yes, the rapid TO actually can be triggered on proposals that are not explicitly declared at the time of the phase 1 application. So it's versatile and elastic just to fulfill this kind of needs, of course.
Thanks.
Great, all right, if you don't have any more questions, let's give another round of applause.
Thank you very much.
And then, do we have Ethan on the Zoom?
Yes.
Yeah, hello. Let me just go ahead and share my slides. Am I good to get started?
Yes, I think go ahead.
Fantastic. Hello, everyone. I'm Ethan Partington from 4th Institute of Astrophysics in Greece, and I'd like to share some of our results developing a new pipeline for significance testing of supermassive black hole binaries, specifically in quasar light curves showing periodicity, using a novel null hypothesis called the null-signal template. So as Maria and Eden discussed in their talks yesterday, in the supermassive black hole binary accretion system, we expect to see a circumbinary disk, and then around each of the black holes, we will see a mini disk. And this is expected to be formed as tidal forces from the black hole shear off the circumbinary disk in a system with an eccentric orbit. This will then be modulated by some factor of the orbital period as this shearing drives mass accretion rate changes, which drive fluctuations in the brightness of the quasar. In systems with very close black hole separations, we will also expect to see relativistic Doppler boosting due to the high orbital speeds, which would also cause an even more smooth periodic trend in the brightness of the quasar. And these are quasars we're talking about at milliparsec separations. So they have not yet merged. They're not in the LISA regime, but they're also much too close together to be spatially resolved, the way that some more distant pairs of AGN are. So these would be ones that are truly in a gravitationally bound orbit around each other and would be the precursors to the LISA sources. Um, Now, to observe these, we are going to need to have very long baselines with a very high observing cadence. LSST is naturally an excellent candidate for this. And we'll also need to take into account the noise of the accretion disk variability itself. As most of you, I'm sure, are familiar, large surveys of quasars, such as SDSS and the PTF quasars, have been well modeled or well described by a damped random walk, where on timescales longer than tau, you have a white noise, and then on timescales shorter than tau, you have this correlated red noise. And the distributions from these that we use in our analysis, our simulations for LSST-like light curves, come from the distributions from the PTF paper in Harizi et al. 2016. So when we're looking at these simulated LSST-like light curves, it's also really it really highlights the importance of having this long baseline and having a limit on the number of cycles that you would consider significant. The current algorithm that we use has a limit of 2 cycles, a lower limit of 2 cycles. More cycles are also acceptable. Because in this simulated light curve, this is a magnitude versus time. You can see that in just the first cycle, it would be very easy to misattribute the variability, this peak and trough here, to some sort of sinusoid shape, when in fact the black dots here are actually a sinusoid modeled in purple plus this damped random walk variability modeled with easy tau. So it's really important that we have a statistical tool that is able to measure the significance of the repeating signals with this presence of this other kind of slow variability that we often see from the correlated noise. So to test the prospects of this type of signal recovery with LSST, we simulate 500,000 LSST-like light curves. 500 of those have an injected periodic signal. This is an estimate of a realistic binary fraction. And then Eden Davies from Washington State University provided the photometric uncertainties and time sampling patterns. She produced these with the LSST OpSim tools. And we stick to the R band because of the higher sampling rate in that band. And then the DRW variability is simulated using easy tau with the parameters from the previous sample that I showed. Now, what's novel about this is we simulate all of these light curves. 500 of them have a periodic signal. And then for all 500,000 of the light curves, we're going to measure the Bayes factor, the ratio of the evidences for some damped random walk plus some signal over the evidence of a damped random walk alone. And we're going to compare these two Bayes factors. In one case, the signal is a sinusoid, similar to the one that we injected, with the phase, the amplitude, and the period all allowed to be optimized over the light curve. And then we also test this null signal template introduced by Jakub Robnik and tested with the PTF dataset. And what this does is it takes an oscillatory function, which is a sinusoid where the period of each oscillation has been perturbed. So you're getting this oscillatory behavior, but it's not on this orbital timescale that we would expect for a black hole binary. And the goal here is to compare the Bayes factor or the log likelihood ratios for the real hypothesis, the positive hypothesis of the sinusoid, or this new null hypothesis of the null signal template. Now, this is kind of an improvement statistically over the damped random walk alone. This is still, the evidence for the damped random walk is still included in this, but it doesn't rely entirely on characterizing your null hypothesis as a damped random walk alone. It accounts for the fact that there may be other variability that has this oscillatory behavior. So we, for all 500,000 of these light curves, measure the Bayes factors for both the periodic and null signal templates, that purple and orange signals that were shown in the previous slide. And we find that in our signal, or in our set of signals where we injected, in our set of light curves where we injected a periodic signal, the Bayes factors are much higher for the periodic signal template than the null signal template. Up top, we have a histogram with the cumulative count, so the number of light curves with a given Bayes factor on the x-axis. And you can see that there is this high Bayes factor tail where the periodic signal template is getting a much higher score than the null template. We also construct a receiver operating characteristic curve. You can see this on the bottom. So this is the true positive probability versus the false positive probability. And this is constructed by raising the threshold of our Bayes factor for what we would consider a detection. So on the right, we have the lowest scores, and then on the left, we have the highest scores. This is color-coded with the bar. And what we see is that the suggestion posed by Jakob Rubnik in his introduction for this method of considering only periodic scores that have a higher evidence or higher Bayes factor than the greatest, most strong evidence for a null signal template, in this case, about e to the 56. Only those ones that are higher than the highest null signal template, we'll call it the null baseline, are considered significant. And we see, because we know which ones of our signals are periodic, that this has an incredibly low false positive rate of 0, and also is a very conservative cut with a true positive rate of only about 20%. What we also find is that most of the null signal template scores here that are performing the light curves with the highest scores are in fact the ones that had a sinusoid injected, and so the null signal template is picking up on this oscillatory behavior. And if we go down to a Bayes factor of about e to the 7, we now get still almost no false positives. It's like less than 0.1%. And we have a true positive rate of about 60%. So this is an extremely conservative cutoff, but it yields no false positives, which is very exciting. And then we also take a look at the ability of the optimization program to recover the parameters that we injected into our light curves. And we find here, this is the same plot, recovered period versus injected period, just color-coded by the log of the Bayes factor, and then color-coded by the signal-to-noise ratio, the amplitude of the sinusoid to the damped random walk. And we find that our periods are recovered perfectly for the most of the quasars with signal-to-noise ratios greater than 1, in suggesting, as we might expect, that the stronger the sinusoid amplitude relative to the noise, the more easily we're able to identify and recover the signal. And we also interestingly find that we get higher Bayes factors for the sinusoids with shorter injected periods. So you can see that here on this color-coded plot. And there's also, of course, some dependence again on the signal to noise ratio. And one possible explanation for this is, as far as the behavior of the shorter period signals, is that we expect that the amplitude of the damped random walk noise is going to decrease. The power will decrease for shorter timescales. So in your short period binaries, the effective strength of the sinusoid on the timescales of interest are much larger than that of the noise. We also use this methodology in the ZTF DR23 sample to test its application to real data. And we end up with about 630,000 total light curves across about 300,000 unique quasars. This is because many of them are observed in the G and R bands. And the starting point for our sample is the SDSS DR16 quasars with confirmed photometric redshifts, who have magnitudes in the GR and I band above the ZTF limiting magnitudes, and that have been observed by ZTF for at least 100 days. So this is a pretty even sampling across the sky and in magnitude redshift space from the original DR16 sample. So we also test the periodic and null signal templates here for these real light curves. Just for clarity, these are split up into the light curves in the G, R, and I band. And unlike our simulations where we had this smoking gun tail of these signals that were very clearly periodic and had much higher Bayes factors than the null signal template scores for the same data set. We find here, using the log likelihood ratio instead of the Bayes factor just for computational efficiency, that the periodic and null templates have very comparable likelihoods in all of the bands. There is this one object out here in the I band that you can see has a slightly higher periodic template score. But if we actually look at this light curve, we can see that in all of the highest scoring light curves for the periodic template, none of them have top 20 scores out of the top 20 of all of the total scores in more than one band. So essentially, we're not seeing this like repeated evidence in any of the quasars that, hey, all three of these bands strongly prefer a periodic model. And in the I band here, you can see this very clearly when you look at the G and R band. This is that one down in the bottom that might have, with a log likelihood ratio of about 45, that might have been considered a periodic by Jacob's metric. So essentially, we don't have any brilliant, exciting detections of a quasar periodicity, as Maria mentioned during her talk. Nonetheless, I think that it's important sometimes to be able to accept the null result here. I think this shows that the null signal template method really is quite rigorous in excluding those false positives. And essentially, where we have some of those light curves that had relatively high evidences for the null signal template, that means that they weren't described strongly by a damped random walk alone. They had some sort of behavior that was preferential for the null template. And we see here, just to show you the highest two scores for the periodic template on top and the null template on the bottom. That these tend to be the highest evidences tend to be for these very long period slow oscillations. Now, just for comparison with the Chen et al. 2024 paper, which identified three potential quasars with periodicity, that paper went out to ZTF DR11. So I've included the original figures from that paper with the archival observations prior to ZTF. The red line is where DR11 cuts off just about, and that's reproduced on my plots here using the data out to DR23. And you can see that in all three of the quasars that I'll show you, we don't have a very high log likelihood ratio for the periodic template. And I think this is largely because after DR11 ended, it looks like the light curves started to depart from that oscillatory behavior. You can see that after the end of DR11 in all three of these sources. So in conclusion, the null signal template is an alternative null hypothesis to the traditional assumption that your signal is either periodic or a damped random walk. And it's more computationally efficient than prior methods, which would require thousands of damped random walk simulations of the same light curve to get some sort of p-value or other statistical measure for how likely the signal was to be periodic. In our simulated LSST-like light curves, the injected signals are recovered very well with a high accuracy and a low false positive rate. And that in the ZTF quasar sample, we don't see any strong evidence for a periodic signal using the null signal template as our null hypothesis for comparison.
Awesome. All right, well, let's go around. Great. So do you have any questions? Yeah, Chris.
Hi. So I was wondering, how big are those mini disks meant to be? Do they have their own broadline region, or is the broadline region associated with the circumbinary disks?
So my understanding from talking to people in Tamara Bogdanovic's group about the actual simulations, is they're expected to be within like 100 gravitational radii. So the traditional accretion, like the broadline region and the outer disk stuff that we would be like looking at in more traditional continuum reverberation mapping and broadline reverberation mapping would be much further out.
Okay, thank you. I was wondering if there would be any spectral signatures, because a very small disk obviously doesn't have the extension down, but I guess the broadline region reprocessing in the winds would mask that.
There's some new work for X-ray spectra that some people in Tamara's group are working on. Because you would have these two different reflection regions, for instance, when you look at the ionized reflection, potentially two different X-ray sources. So that's stuff that we would need like much higher resolution instruments to detect, or variability studies over very long times, like over, the timescales of these like orbital oscillations. That I'm less well versed in, but there are some interesting papers on it that I can send to you. But as far as the optical and UV like broadline spectra, I think that it would be possible for the like basically for those to be hiding in plain sight, so to speak.
Thank you.
Yes, okay, Ilson?
Yeah, thank you. Hi, Ethan. Very nice presentation, which is, yeah, it's a very interesting idea. Then I was wondering, could you more elaborate on the null signal template? You said it's a perturb.
Mhm.
Yeah, I don't know how it perturbed. Then because I'm asking this because if you consider the one band, I
Mhm.
mean, it could be the alternative hypothesis, but if you combine the multi-band, for example, have a different lags, for example, in the
Mhm.
observing cadence, I mean, they're also mimicking the same, but similar behavior, I think. So I just wanted to know, when you say that the perturbed the periodicity, what exactly you do?
Yeah, so essentially there is for each of the null templates, there is going to be some mean period, and that's what gets optimized over, just like the period of the sinusoid is kind of optimized until you get the one that fits the data best. But then for each oscillation, that mean period is modified by some factors. So the first seven have been fixed by Jakob to minimize overlap between the null signal and a regular sinusoid. So you'll see that this one, the first oscillation is about half the mean period, and then this is maybe twice the mean period. This is closer to the mean period itself. So they're all modified by some factor. And then as you go beyond the first seven periods, it's all randomized. So we use a random number seed for everything. And then we're comparing the performance of the null templates with all of these random instances over the entire sample of light curves, essentially showing, rather than doing like the thousands of simulations for each one, looking at the behavior of the population. And we do right now treat all of the bands independently, so they are each fit without any knowledge of what band it is, just based on the variability fitting the periodic and null signal templates. There's the possibility, like you say, to kind of combine the bands and try to find some sort of underlying signal that is common to the multiple bands. But as you say, that would run into problems like, potentially lags between the different slow variabilities. So what we see in our highest log likelihood factor signals, at least for the periodic template, is that they tend to identify at least the same period or similar periods, if not with the same level of evidence. And then the null signal templates, I haven't looked into the specific comparison for these ones. But I hope that that sort of starts to answer your question.
Yeah, thank you. So also the very small question, when you say the base factor, are you computing the base factor based on the full posterior samples?
So it is, it's, what do you mean by the full posterior samples?
I
Just
mean, the
to,
base factor basically is the ratio of the marginal likelihood, right?
Yeah. So it's for each light curve, the ratio, including all of the data points in the light curve of the marginal likelihoods, the likelihoods weighted over the prior for the periodic signals, which get a prior based on the gravitational wave evolution that we expect for periodic or orbiting black holes. And then the prior for the damped random walk only has like a normal distribution around the input guesses for the parameters, I think. But it's just calculated using all of the data points in the single light curve. It doesn't like look at the other light curves at all.
Yeah, okay. Okay, thank you.
Mhm.
I think we gotta move on to the next speaker, so we'll give another round of applause and if
Thank you.
you just want to join in Zoom and share screen. You can, if you want, put you up. Love you to
Hello, everybody. My name's Raphael Shirley. It's a pleasure to speak to you today. I'm a postdoc at the Max Planck Institute for Extraterrestrial Physics, mainly working there with Mara Salvato, also working with Johan Cohen-Tanugi and Olivier Hilbert, both based in France. Today, I'm going to be speaking mainly about photometric redshifts and the work I've been doing particularly on LIFAR over the last 2 years. So to give you a quick overview, there's less than 1 year left of the German in-kind contribution that I've been working on since early 2023. And the key focus of this work is eROSITA, so the X-ray all-sky telescope eROSITA. And we're looking at counterparts and photometric redshifts for these X-ray sources. I think hopefully the LIFAR for AGN module that I've been working on will have much wider applicability beyond those X-ray samples. So a key focus of the work has been the rebasing of LIFAR into a C++ code with Python interface, integrating that into what's called the redshift assessment and infrastructure layers. Rail, that's a code that is developed by the Dark Energy Science Collaboration for computing photometric redshifts. And we've also done a lot of work in our group, in the high energy group, on machine learning methods. And I'm doing a lot of work on comparing machine learning methods to LIFAR and trying to understand where each is preferable. I've been testing against the clouds data set, something else I'm going to talk about. And then finally at the end, I'm going to talk about work I've started doing on DP1. That's obviously very early work. So the eROSITA data is this all-sky survey, as I mentioned. This is what's called ERAS-1, the eROSITA all-sky survey. And this is the first pass that was released in 2024. As many of you know, it was due to do 8 full passes of the sky. Unfortunately, due to the war in Ukraine, it stopped halfway through. But those 4.5 passes will eventually be released. But at the moment, we do have this first pass. And in particular, we have the German sky. So the sky was split in 2. And the Western Galactic Hemisphere is available in public now. This is exciting, of course, because it has a very good overlap with Rubin. So very large areas of the sun sky, we have this relatively shallow compared to the deep X-ray surveys, but we have this very wide area X-ray data. I quickly want to talk about the problem of counterparts. This isn't something that I'm specifically working on, but it's a key part of the in-kind contribution. One of the key problems with X-ray data is we have this low positional accuracy, essentially. That means there are many possible optical counterparts. In Rubin, where you've got this almost 50% of objects are blended, you've got a huge number of counterparts, and that's why Mara had to develop this N-way code for Bayesian cross-matching. Essentially, you learn from the color space, the colors of your counterparts, the probability of a given object being an X-ray emitter, and then you use that to calculate which counterpart is most likely to be the X-ray counterpart. And here, these 2 figures I'm showing you. So W1, W2 against W2 color space. And again, how you learn from a set of objects which only have one counterpart and therefore effectively accurate counterparts. You can learn this prior, learn which of those areas of color space are more likely to be X-ray emitters. And these ERAS-1 counterparts are due to be released imminently. This Salvato al paper in proceedings, in process. And for DP1, DP2, DR1, I think it's fair to say what we'll be doing is we'll be taking those counterparts, which is a legacy survey, and we'll be just directly cross-matching those to LSST using a direct cross match. In due course, it's our hope there will be N-way rerun on the LSST objects with LSST colors. But for now, for these early data sets, we'll be taking those matches to legacy survey. So the focus of my work, as I said, is photometric redshifts. Just to give a little motivation, I think it should be clear to everyone in the room how important photometric redshifts are. If you want to do any sort of demographic studies or look at individual objects, we obviously require redshifts. So we want to look at the relation between star formation and black hole growth, for instance. We need redshifts for all those objects. We'd also like to have physical properties for those. And of course, the difficulty is that the spectral energy distributions of AGN, we have fewer broadband color features than typical galaxies, therefore typically have lower accuracy, and that's an ongoing problem. We also, of course, have a large dependence on the selection method. So we have some X-ray selected or mid-infrared selected or variability selected AGN, and all of those are going to have different properties. When we select template sets, for instance, to run photometric redshifts through the template fitting methods, it's important to use a different template set and different priors for all of those selection methods. Or if we're using machine learning methods, we probably have to train on those samples independently because they have very different properties. The relative contribution of the host and AGN is, of course, unknown when we see the data directly. That adds a level of complication, and also obscuration further complicates some objects. We might be dominated by the host, and therefore the galaxy templates will work very well. That's just to give you an overview of the complexity of the problem. I always show this slide just to say that machine learning methods and template fitting methods both have advantages and disadvantages. And I think a real focus of our work is trying to use them both together. That's where this rail infrastructure, I think, is very important. So to summarize, machine learning methods have very high performance inside the training space, very easy to use additional inputs. You can put anything in there, you can put colors, you can put aperture measurements, various measurements, anything you like essentially, and it's very fast to run after training. I think the downsides though has poor handling of rare objects. So if you don't have many objects in your training space, they won't perform well, and they require retraining every time you have new data. Anytime you get a new survey release with different error properties or etc., they need to be retrained. Template fitting, the real benefits is physically motivated. So we have a set of physical templates which we're fitting to the actual data. That means we have no training set requirements. We therefore have no training set bias. That allows us to probe new regimes. It's statistically robust, essentially Bayesian statistics are very well understood. We don't have this problem of perhaps the sort of black box nature of some machine learning methods. But we, of course, require very accurate measurements and errors, and the data has to be very well calibrated. If you arbitrarily add one magnitude to all of your magnitudes in machine learning, it won't affect the results. But of course, that completely ruins your template fitting code runs. But that can be a benefit, and it's a means to check the quality of the data as well. So the real focus is using both together. With that in mind, I just want to quickly promote some codes that have been developed in the Energy group and the machine learning side. Like I said, it's not the focus of my work, but this circles code, which takes the aperture photometry. And what we found is that by using the full apertures independently, you can essentially disentangle to some extent the AGN contribution and the host contribution. So you can use that very informative color information from the host to get high accuracy photo-Z. And this is what we're using for the legacy survey counterparts, the ERZ release, which is coming up shortly. And I think the exciting thing about this code is it can very easily be extended to LSST data. And hopefully we'll have a project at some point doing that. That was by Aman Saxena, to mention the lead author, a student who was in the high energy group. Another code is the pixel code. It's developed by William Rostow, also in the high energy group. And this extending that idea takes the full pixel information. So you're still doing something similar where you're taking advantage of the fact that you can disentangle the host and the nucleus, but you're really using every pixel so you can get even more information, including from, for example, the shape. And this code is now fully public. You can do pip install pixel. And that ships with models. And again, this was trained on legacy survey data, but is very easily extended to LSST. And again, we hope that we will have people to do that. My focus has been on FAR. As I mentioned, this is a template fitting code. It's a very well-established code, originally written in Fortran, going all the way back, I think even to before 2011. That's the main paper presenting it. Essentially, it's spectral. 2006, okay. Essentially a spectral energy distribution fitting. There's a new C++ version, which I've been focusing on. There's a Python interface, as I mentioned. There's a Rail interface. I'm going to talk more detail about Rail. That's been a key part of getting LeFar to be run on large numbers of objects. And we fit stars, galaxies, and AGN separately. So we have a separate set of templates for all of those objects. And essentially, it's a chi-square fitting method for each of those template models. The redshift assessment and infrastructure layers is a computational sort of set of software tools for running at scale and doing point estimate performance, as well as looking at the full posterior. So for every object, we produce this posterior here on the redshift. Then we take, for instance, the median, compare the performance of those medians to spectroscopic objects, and then look at the plot on the right here is what they call a probability integral transform. That's a metric for how well the posterior is performing. There are creation algorithms in Rail, so you can produce fake data. There are methods for degrading those simulated catalogs. This is a sort of key focus for the dark energy science collaboration, that they have all these methods. But the impact of LaFar is as what's called an estimator. And the real advantage here is that by putting LaFar in Rail, anyone can just switch it on when they do Rail runs, and they have it as a comparator. So you can see there's a large number of methods implemented in Rail, a couple of template fitting methods, but I think the BPZ, for instance, has by default a very simple template set and has a lot fewer features in terms of physical modeling compared to LaFar. So I think it's fair to say LaFar is really the most sophisticated template fitting method that's in Rail. And that addition of a template fitting code, I think, is a real advantage for Rail, both for the dark energy science collaboration and I think very importantly for AGN, for reasons I'll explain later. I was very excited to see that LaFar estimates are in the Rubin Science platform. Thanks very much to Tianqing Zhang, who did these runs for Desk, and to Nevin Kaplar, who put them in the LSDB interface on the Rubin Science platform. So the first thing we did, as the example notebook here, was look at comparison to DESI spectroscopic objects. And these are galaxies, so I think these runs were done, as I said, for the Dark Energy Science Collaboration. They're all focused on galaxies. They've only made the galaxy template estimates available. But the nature of LaFar is that those runs will have also included AGN templates. So I think there's a sort of a slight political question there that we'd really like to make those AGN estimates available as well, including conceivably the posteriors. So Rail produces posteriors for every object, for every method. We are, of course, also generating these AGN posteriors, and they're very useful. I think also that experience has shown that these can still be useful for low AGN fractions and type 2 AGN, anywhere where you're host dominated. These galaxy estimates can still be very useful. So I'd like to have a quick slide on the products that we're going to be releasing. As I mentioned, the Rail runs by Desk. They include point estimates and quantiles for all the methods, but for one posterior only. So it's a question about how exactly these posteriors are distributed. Can we make those available to everybody? By default, we've just got relatively low density quantiles. But I think I've heard that there will be 100 columns available for photometry redshift. So I think it's time for us to start thinking about what those values are going to be, how many quantiles we'll produce, which are the key codes we'd like as the AGN Science collaboration. And yes, a key part of the AGN runs is running with multiple sets of filters. So we use extendedness to split the samples, for instance, to determine whether we're hosts, we've got a large host combination contribution, or whether we're AGN dominated. And I think understanding how to use those extended measures in the early data is important focus on my work at the moment. We will be conducting our own runs on reduced AGN candidate lists. I'm particularly looking at X-ray samples at the moment, but conceivably if we work on a combined AGN selection from the science collaboration, that could be a really useful thing to run on. But crucially, I think we're not planning on doing large runs on every object, not on 40 billion objects. We need to run on smaller samples to do multiple runs with different template sets. The work that I've really been doing recently, which is going to be published shortly, has been on the clouds data set. So this was, they did U-band imaging from the Canada, France, Hawaii telescope, and they've added that U-band to Hyperspeed PrimeCam. So that's produced this UGRI-ZY data, which is therefore comparable to LSST. And we've been concentrating on the cosmos field because we have both excellent spectroscopic data, we've got excellent X-ray samples, and we also have excellent photometric redshifts from the 30 bands of cosmos, which has been really important for us for testing the performance of the methods. So to show you the filters here, I've got in yellow and red on the left, you can see the LSST and clouds filters. I think they're quite well matched. We were also looking at the impact of the near infrared, where we have Vista currently available. We now do have some Euclid data available. The Euclid and the Vista bands, I think, are more significantly different. So the Euclid bands are quite wider. And of course, in Vista, you have this K band coverage that you don't have in Euclid. And then if you look at the color tracks, so U minus G against J minus H on the right there, you can see there are differences, but we're still getting a similar area of color space. So it's still a useful comparator to see sort of in general terms what the impact of the near infrared is. The first thing we always test is performance on galaxies. So I'm showing galaxies straight away to just demonstrate the baseline performances. This is compared to various machine learning and template fitting methods. And I think the summary I always have here is that we're comparable to the machine learning codes. The performance is usually slightly lower, and that's something we expect. But that is sometimes due to this issue of training space bias. And I think quite quickly you can see as you move out of the training space, you start to see much more competitive performance from template fitting. And then again, showing the same data for AGN. And of course, as we expect, we do see much lower performance. So seeing outlier fractions of around 20%. The machine learning codes can go as low as 17%. And these machine learning methods here were trained on the full sample of galaxies and AGN. So it's still quite impressive that they can, just by you don't tell any information about whether an object is a galaxy or an AGN, you just give it the redshift. And we're still seeing reasonable performance there. There's a lot of details in those performance comparisons. I think the key comparison here is between the addition of the near infrared and how we are seeing higher accuracy when you add in near infrared for these X-ray detected samples. I think I'm going to hurry up a little bit. So I just want to very briefly say the work on DP1 that I'm starting to look at now. I'm looking at both the ECDFS and the EDFS fields. These are the sort of key extragalactic fields where we have useful information we've got useful X-ray samples, particularly on CDFS. But this is the full extragalactic data set that we're working with now. So this is what I'm working on at the moment. And as I said, the first thing I'm doing is looking at galaxies, but I'm also focusing on this, particularly the X-ray objects. So William Roster has produced this set of X-ray counterparts for Euclid. That's a key focus of the work I'm doing on DP1. So my hope is really to publish that this year, is to produce 4 the X-ray counterparts selected by William for his combined both XMM, Chandra and eRosita. And trying to produce a kind of an X-ray AGN catalogue for DP1, and that's the paper I'm hoping to work on in the next 2 months. And those first investigations, I'm running on a selection of public galaxy spectra just to check again good results for galaxies, to check that the photometry is working as we expect. Then, as I said, looking at X-ray samples and possibly thinking about larger runs, producing a prototype LaFar AGN photosea catalogue on larger numbers of objects. And then looking at various possible sample selections on that DP1 data, conceivably also looking at variability samples or color selected samples. I think, yeah, that's just to conclude. I think machine learning, template fitting, both going to be useful for AGN science. The FAR is available with Galaxy templates on DP1 data. And yeah, just to promote this new version of LaFar, you can install it with PIP alongside the Pixel code developed by William Roster. They're all public, and we'd love people to be using them and testing them. There's a rail interface, which is allowed the FAR to be run at scale. And I've started work on DP1, looking at the X-ray counterparts from William Roster, and also looking at public spectroscopic samples, and the possibly Euclid AGN candidate samples as well.
Great. One quick question, but maybe we can have the next speaker come up and start getting set up.
So for EDFS, which data in your IR you use? Euclid data?
We will be using the Euclid data, yeah, the Q1 data, yeah.
We have a K-band also in the Vista, but it is new and released.
Your paper, yeah, I mean, we could test Vista as well.
Yes.
That would be interesting.
Thank you. Awesome.
Thanks so much. All right. Yeah, there's another round of applause.
Should I just start?
Yeah, go ahead.
All
Yeah,
right.
sorry.
So, yeah.
Formal here, yes.
All right, so I'm Claudio Ricci. I'm a faculty at the University of Geneva in Switzerland. And I recently actually got back to Europe after spending over a decade in Chile. And I'm going to tell you about some of the ideas that we have to study changing state AGN with LSST. So starting with a little bit of an introduction, just to remind you what changing state AGN are. Those are objects accreting supermassive black holes that transition from type 1 or type 2. So you have broad Balmer lines that appear or disappear, as you can see here in this case. And this usually happens on relatively short timescales. Those objects are very interesting for a number of reasons that I will be showing you today. But one of the main points is that we still struggle a bit to understand what's going on in terms of like these lines transitioning, as well as the timescales being so short. So what triggers changing state events? This is something we heard about already on Monday. There are two main possible explanations the way I see it. One I like very much, which I think applies to actually most subjects, are state transitions. And those are very similar to what happens in black hole binaries. So this is an idea that was put forward by Noda and Dunn already a few years ago. And the idea here is that when you have a change in the accretion rate, basically, like let's look at the black line, you're in a high pace, so you have a strong continuum that you can see here in the X-rays that extends down to the optical UV. This produces a very strong emission at tens of electron volts. And these photons are the ones that are actually able to photoionize the material that then produces the broad line. As the accretion rate goes down, so here you go from the black line to the red and the green and the blue, what happens is that your accretion flow transitions to an advection-dominated accretion flow. And so you're losing the inner regions of the accretion disk. Your SCD becomes much less blue, let's say. And so you lose a lot of these optical UV photons, and therefore you lose the ionizing flux that is typically able to produce these broad lines. And this is something that I think can explain very nicely a large fraction of the objects we see. The postulate here is that you expect a transition to happen at an editor ratio of about 1% or so. So this is a number to keep in mind. You probably already heard extensively from Chris about it. The other possibility that I think applies to several objects, it's much more rare, is that you have these perturbations. This can be, for example, associated to TDEs. You have an accretion event. So basically a star is entirely disrupted and ripped apart by a supermassive black hole. And what happens is that you have extra gas, extra accretion, so you can increase the flux. And this gas that is actually taken from the star would eventually produce also some broad lines. And one clear example of this is SDSS J0159. This is a source that was shown by Andrea Merloni and collaborator 10 years ago to show a decrease in flux. So this is the intrinsic continuum, most galaxies obstructed. And this decrease goes down, this emission goes down with a trend that is actually proportional with what you expect in tidal structure events. So this was a good indication that this might be the case, at least in some objects. Another case in which this might apply is 1ES 1927. Those of you who know like what I do know that I've been struggling quite a bit with this object together with many collaborators. This is an object that was originally discovered by Benny Trachtenberg. And this is a source that was picked up by Assassin originally to have a very strong increase in flux. So here you have the magnitude as a function of time. You can see that it went up and then it went down again. And I won't go into details, but there are a lot of properties of this source that make us think that something very extreme, such as an external object plunging into the accretion flow might have happened. And this all happened at accretion rates that are way higher than the 1% that I mentioned earlier. So this is something extremely different from the classical changing state AGN that we see in the local universe. All right, talking about local universe, I do like to study nearby AGN. Sometimes I regret it because it doesn't make them easier to understand, but at least it's easier to get data. So this is some work that was done by Matthew when he was in Chile a few years back. We took a large number of Swift bat AGN, about 400, for which we had repeated spectroscopy over the years. And then we went, Matthew did all the artwork. Matthew went and checked how many of them actually are changing state, and he found about 20. And the interesting thing is that he found that also this the broadline phase associates with higher flux. And here I'm showing a couple of light curves. This is the flux for those of you who are not versed in millicrobs as a function of time. And L here stands for narrow line and BL for broad line. And you can see in the case of here of NGC 2992, it's very clear that you have broad lines when the flux is high. On the other hand, here you have a decreasing flux. This is NGC 3516, another very well-known nearby AGN. And as the flux goes down, you have a narrow line phase. Then the flux goes up again and goes down. And here you have broad lines, but probably just because the material hasn't had the time to respond to the changing flux yet. And what Matthew found was that basically somewhere between 0.7 to 6% of the AGN from this sample from the BAT survey were shown to actually display these changing state transitions on timescales between 10 to 25 years. And the typical timescales of these events are somewhere between 3 and 10 years. And as I mentioned, this is a bit challenging to explain with typical accretion models because it's way shorter than the viscous timescale. So where do we put this object then in an Eddington ratio Blackburn mass plot? This is shown here. So those are all the BAT AGN from Matthew work. And colored here, you can see the changing state event. And you can see that most of them actually live in this region. So we're between 10 and 0.1% of Eddington. So we continued this work with another postdoc working in my group. This is work done recently by Jana. Was done also a lot of heavy lifting in this studying this object. And here I'm showing you the Eddington ratio as a function of the spectral type for two objects. And you can see here that you have a transition. Let's call this type 2-ish and this type 1-ish. And the transition happens again at a few percent of Eddington for both objects. And then we can do some statistics from these 20 objects. And here we have this transition Eddington ratio, which is the place in the Eddington ratio space where you go from narrow to broad lines for different transitions. So here you have 1 to 1.8 to 1.9 and 2, 1.8 to 1.92 and 1.9. And you can see that there is a spread, but most of the transitions actually happen at a few percent of Eddington. So those are the typical transition Eddington ratio, and this again, it's nice and consistent and makes Chris very happy, I guess. So we continued this work very recently, and we have been studying the X-ray and multi-wavelength emission for all these nearby changing state transition. So again, this was a lot of work that was done by Argajit, in which he collected over 1,000 observations for a handful of very well-studied changing state transition. And what he did basically was to create SCT. This is part of some work that was done within my group. So we have OS galaxy, well-characterized OS galaxy magnitudes in all the Swift and XMM filters, which allow us to basically remove any contamination from the host and to study the intrinsic evolution of the AGN SCD across these transitions. And what we have been seeing is that basically there are very strong changes in these SCDs. We have been using very phenomenological models to be as agnostic as possible into what is causing them. But we do see a very clear changes. And this brings me to one of the main reasons I think we should study these objects, is because they give us, since they vary so much across several orders of magnitude in luminosity on rather short times, they give us the possibility of actually studying accretion physics for just a few sources across wide ranges of luminosity and Eddington ratios. Here I'm going to give you a couple of examples of what this is good for. So for here you have a very well-known correlation between the photon index and the Eddington ratio. This is for the BAT AGN. There are many of these plots. This is work that goes back, dates 20 years from the original work of Schemmer, I think when he was working with Neil. And there is a correlation. There is a lot of noise, obviously, and it's been proposed that actually you have a break in this correlation. Now, for many works, this is statistically significant, but you agree with me that here, I mean, one needs to be a bit careful because the errors are very large. So what happens now when we do the same thing with changing state AGN, just using a handful of sources for which we have studied very well the SED variation. This happens. So the scatter is very reduced here, the scale is much smaller. And basically we can see this V behavior very clearly. This is only 5 objects for, as I mentioned, about 1,000 observations. You don't have 1,000 points because things were grouped, but it very clearly shows us that indeed there is a transition in this photon index at interration. Another thing that we studied and that one can do to showcase the power of changing state AGN is the relation between soft excess, so it is excess in the soft band below 2 kV, and the Eddington ratio. Again, there have been some claims. Some of this is statistically significant. Here you have on the y-axis various indicators of the relative intensity of the soft excess as a function of the Eddington ratio. You see, there is again a lot of noise. There is a trend, but what happens when we actually do this with changing state AGN is bad. This is very clear. You agree with me? This is way better. And here we are covering over 2 orders of magnitude Eddington ratio. Again, this is only a handful of objects. The correlation is very significant, and in particular, when we go towards the low accretion rates, we see that we recover mostly upper limits. So basically the soft excess disappears. And this goes together very well with the idea that this is what's powering this changing state transition. So now here you have the type 1s in blue and the type 2s in yellow. You have a little bit of overlap. And this is mostly due to the fact that often enough our spectroscopic observations happened at a time in which basically like the change in flux had already happened. So it was a bit hard to couple the type 2 to the observation. And so like we actually tried to put the type 2 and type 1 classification to the closest observation that we had, but often enough there is some confusion because we had gaps obviously in our light curves. But this seems to work very well, and the soft excess disappears at like a few percent of it. All right. So what can we do now with LSST in the future? This is something I'm very excited about. There is going to be a lot of work possible to do this sort of study. So to study accretion physics for a few objects in the local universe, but not only to understand in detail what's going on with our beloved AGN. So in particular, let's start thinking where to find this changing state AGN. So this is something also Chris mentioned. If we are looking for state transitions, we want to go at a few percent of Eddington. Instead, if we are looking for the weirdos, so the things that explode like 1S 1927, we might want to move towards lower black hole mass and higher Eddington ratios, because those are probably the regions where you have tidal disruption events and things of this sort. So for the changing state AGN, actually, this is going to be easy. I'm showing you a local Eddington ratio distribution function. So this is the density of AGN as a function of the Eddington ratio. This is for nearby object. And you can see that actually we are quite blessed, at least this is for the local universe. We are going to have really a lot of objects in this region, and obviously it's going to be much more difficult to find the rare transients and the exploding things. That's our problem. So how are we going to identify them? Well, obviously with flux changes, this is going to be the first requirement. But also, since now we have this rather well-defined spectral energy distribution, we can start to think about doing something like studies of color variations from the SED and feed the SED into the machine learning. This is like in agreement, I mean, in the same direction of the work Paul has been doing over the past few years, but now we have like some data-based SED, which we can use for this sort of ways. We are not only going to have to deal with changing state AGN, there is much more going on. This is a beautiful object, something that is it's been studied very recently by Paula Sanchez-Saez and Lorena Hernandez Garcia. This is an AGN, it's an object that had no AGN, then all of a sudden, boom, AGN, decrease. We went and looked at it in the X-rays, QPs. So yeah, I mean, there is plenty of stuff like this, I think, that we are going to be finding out. Plenty of headaches waiting for us. So how are we going to deal with all these? Obviously, the resources are going to be very limited. We need to identify and follow up these objects. So with Bin Durrani, I'm leading the follow-up working group, the sub-working group within the AGN collaboration. We have a breakout session tomorrow in which I'm hoping to discuss, we have at least a couple of big proposals we want to write, and you're all welcome to join. We are going to talk how to deal with these objects with brokers, but also like how are we going to do optical follow-ups, and in particular, we are going to do follow-ups with for optical UV and X-rays using various facilities. Just to wrap up, what questions we will be able to address in the next years, thanks to LSST and all these studies. Well, we're going to start looking at demographic of the state transitions and to understand why some objects they show the state transitions and others maybe not, but or maybe they all do when they transition, they go around a few percent of Eddington, but it's true that not all of the objects that are around there display these events. So this is something that I'm very curious about. We are going to be studying the demographics of this perturbation, since this rare population is going to be better understood and certainly find a lot of rare and exotic AGN transients. And I think, like, particularly looking at the exotic transients, these are often enough transformational episodes that really can tell us a lot about the formation of AGN, because, you know, if you lose an accretion disk and then this reforms, you can learn how basically the recipe for creating an accretion disk or close enough. And I didn't speak much about 20S, but stay tuned because there are some even more surprising results coming up. These objects are really phenomenal because there is a lot of different things happening. So I'm going to leave you with my summary. Just remind you, tomorrow we have this dedicated session, so you're welcome to discuss about the results.
Great, Nevin, you wanna?
How will you, like, what would you search for in LSST to identify candidates? What is like your plan?
Yeah, so the first, I think, like, it can be a multi-layer recipe. The first one would be like a strong increase in flux, but that depends how it's defined. But like, let's say we decide to select only things that go up of a magnitude in weeks or months. Then we are going to be wanting to introduce colors, if we can, as a second layer. Because eventually, I mean, we cannot really follow up. And I think this is a lesson learned also from other recent surveys. There is a lot of events, you have limited observing time. So yeah, you need to make some sometimes tough choices. But yeah, I think we'll start with flux and color selection. Color changes.
So apart from making me happy, the changing state, they give us insight into the biases in what we've already put in to our prescriptions. So when we get black hole masses, if we do it from reverberation, we're assuming something about photoionizing spectra, and that's not going to work the other side of the transition. So even reverberation mapping can give us horribly the wrong answer if we've got a very different. Can we select out a sample of objects where we can look at them each side of the transition? They obviously haven't changed black hole mass, and it can start to give us some insight into the biases that we get when we're doing masses for the AGM below the transition.
Yeah, there is certainly plenty of objects around there. And actually, it would be curious to look. No, but it would be curious to see, because if you look at these objects from Matthew, actually a lot of the gray points, they have reverberation mapping inferred masses.
Yes.
I don't know if there is any active campaign, but yeah, maybe observationally expensive, but yeah.
And this time just.
Yeah, quick question, and then maybe Marta can come in.
Yes, so on the slide, no, I need to.
Okay, sorry.
The presentation slide, the title slide.
This.
No, this really the title.
This.
The next one, sorry.
This
one. Is this a real object?
No, but this is based on a real object. This is based on one of the SDSS, the one from Richard
But it is
Zelda.
a real.
Yeah.
So I am probably too tired and say something extremely stupid. We look a lot at the change that you have in the broadline component between the two phases. But what is striking me now is that the intensity of the H and K lines are the same, despite having the continuum that pop up dramatically.
Right.
How is that possible?
Yeah, I don't remember if in his paper Richard discussed this, but it's in Zeltin 2022.
Okay.
So this is like a CSS something.
I've noticed that as well.
Huh?
I've noticed that as well.
So you're
Yeah.
also puzzled by that?
Yeah.
Because
Yeah.
it's, even the emission line, I mean, that is weird. The observed
Right.
line should not be there.
Okay,
So,
but yeah, probably it's in his paper, I honestly
Okay.
don't know.
Yeah, we can check it out on the copy break. Let's get our last speaker up here.
sì, sì, sì.
Okay. I'll give you 2 moments and then let me talk about these things.
Yes, hi everyone. My name is Marta Patovic and I'm currently a postdoc at University of Naples in Maurizio Paolilo's group. And today I'm going to present Time Dome's in-kind project. I will give status update and show some first results. So first things first, what is Time Dome? So this is short for Time Domain Surveys. PI is, as I mentioned, Maurizio Paolillo. The main scientific goal is census and characterization of AGN populations through optical variability in 4 of LSST Durham fields with the data observed with VST. Now very briefly about VST. It's 2.6 meter wide field optical survey that observes southern hemisphere, has one focal plane instrument called OmegaCam, and has field of view of 1 square degree. Okay, so before Time Dome's project started, there were already data, there were already observations, of PST observations of 4 of the deep drilling fields of interest, which are LIS, Cosmos, XMM, LSS, and Jana Deep Field South. They were performed, done in the framework of some other surveys. And what is the main goal of Time Domes is to expand those observations, so both temporally and spatially. So here we can see how these other surveys saw these 4 fields, and now we can see how Time Domes sees them. So we have 4 square degrees of observations for these four fields. When it comes to temporal expansion, here are the histograms of the epochs that were taken for each field. So for example, for Cosmos field, we have observations that date back to 2011 up to 2015, and then we had some gaps, and then the Time Domes project started in 2021. So this part is part of the Time Domes project observations. That is in GNR band, just to say that out loud. All the same, the very similar story with Chandra Deep Field South. So observations up until 2016, 1 year of pause, a lot of observations 2018, 4 years of pause, and the Time Dome started. The story is a bit different for LIS and XMM LSS because there are very few observations, if any, before 2021, before the observations for Time Domes project started in G and I band. So we can maybe say this is maybe the first time in these filters that we have these observations. Okay, current status. As I mentioned, the observations are still ongoing. We are getting more or less of 2 epochs per month per visible field. currently, if I'm not mistaken, two of the fields are up on the sky and getting observed. One is also getting up, so soon it will be on the sky, while Cosmos is part of the other part of the year. So this observational mission is planned until the end of this year to have some overlap with LSST, because we are all very interested in LSST, and we are planning to cross-match our data, and of course to expand our baseline and to see how well we were doing. The data reduction is ongoing, painfully, but ongoing. We managed to improve a lot of things. Here is the example. This is the same epoch of the same region of the sky. I'm not sure if it's seen, it's presented nicely here, but on the left-hand side was the date. This epoch was reduced like 9-10 months ago, and it was the best that we could do then. Then we collected some wisdom, and we improved it like here. Still, it's not perfect. As you can see, edges of CCDs are problematic. We have some reflections, but the improvement is obvious. This is just, I wanted to put this image to show you that how this part of the sky, for example, zooms in, how deep it goes. Also, we are aiming for 5% data accuracy. What I mean by that, so each epoch gets compared with the reference visit, and then we calculate the scatter between 16th and 21st magnitude for that epoch, and this is what we call accuracy. This is one of the best epochs because nobody comes to the conference and shows the worst one. So this says the accuracy is around 2%. However, not all epochs are like that. Some are incredibly good, some are okay, some are good, and some are less good but still good. This is the plot that shows how this standard deviation, how does this accuracy changes over the visit number. So basically what we can conclude from this plot is that all of the visits in this subsample that I've chosen, this is I think CDFS, are below 5%, which is good. And then you ask me, okay, but what are these two red dashed lines? And then I tell you, okay, maybe I lied a little bit. Sometimes the accuracy is not that good. Sometimes epochs are faulty in a sense that the night was bad, there was bad air mass, maybe they had some faults after the data reduction that we couldn't understand. So still we have 2 epochs among 20-something epochs. So this is, at this point we can say, okay, we can just exclude these 2 epochs and continue with our work. When it comes to challenges, there are a lot of them, but these are the most important ones. First of all, we are getting a lot of observations, so we have to schedule the observations, and then we are getting those observations while still processing the data from 2024, so the data are piling up. So this leads me to data reduction, which is the main bottleneck for our project. We have a lot of issues with stability of the database and the pipeline. So pipeline physically is in Groningen, it's in Netherlands. So what we need to do is basically connect via VPN to the observatory in Naples, and then from them to Groningen, and these connections always break. So it's not sometimes, it's always. This is why we cannot just write a script, even though we have a script, but we cannot just run it on a bunch of data. We have to do it more or less manually, in a sense that we copy paste each line, and we are physically there to see where it broke so we can fix it. So in that sense, it takes a lot of time. However, data reduction is done actively in our group in Naples, but lately we've been getting a lot of help so 2 of our colleagues are helping us a lot, which are called Barbara Balmaverde and Mario Radovic, and I would like to thank them a lot for saving me of pulling out my hair. So this is now getting better and better, and we are getting faster. Another one of the challenges is photometric accuracy is still problematic in some epochs, but we can say it's not in a lot of epochs, it's like few of them, so for now we are okay with that. Another thing worth mentioning is that masking of the problematic areas is done still manually, which is time consuming, but not terribly. Okay, when it comes to deliverables, we are going to distribute this data, and the data release will be incremental. First large chunk of the data up to 2015. If you remember, I showed you that there are a lot of observations of Cosmos and Chandra Deep Field South. We are going to release now. So you can scan this code, the data are there. We will, of course, distribute it officially, but there are two things to say about this particular QR code. So currently, the data are stored on Maurizio's server in his office, which has terribly slow connection. So the download speed is terribly terrible. However, we are solving this problem. Maurizio is really working hard on it to move those data to data center in Naples, the one that Ak and Angela were mentioning before. So it will be properly distributed, but we were getting anxious and we wanted to distribute what we have so far. And the second thing I wanted to say, the second thing is the data are there, all the data that are going to be in first data release. However, if you're not in a huge hurry, maybe wait for next week when you will get some other things like a properly written README file. Maurizio is working on that now. So yes, some other tweaks will be done by next week. So the rest of the data will be released incrementally, starting from autumn. So of course, stay tuned. And what we will share images. So images of single epoch images, some stacked seasons. So in this first data release, this is a preliminary data release, we are going to share only images, single epoch images, some stacked seasons, and we will share these 2D maps, which will tell you how the data quality changes across each field. But in the next data releases, we are going to release light curves. This is just one of the examples that I got like a few days ago, so I was happy about it. This is still work in progress. We have to test some things. I hope it will be done next week, maybe 2 weeks, 3 weeks, but we don't know when we will release them. Probably after summer with the rest of when we start releasing other parts. So. Also, what we will distribute is the code to extract those light curves. I'm trying to make it the most automatic possible, so you can just use it like click, 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 you get your light curve. However, you don't have to use it. You can use your code, whatever you are used to. It's going to be there, so if you are willing to use it, go ahead. Okay, the ongoing scientific. So, our group mostly focuses on selection of optically variable AGN with multiple epochs and characterization. I'm not going to talk about this because Demetra gave an amazing talk on Monday about this. Right now, I will tell that we are working on homogenizing the whole approach. So homogenizing the whole approach using other fields, not only Cosmos, and in multiple filters. And these are conclusions. So there are a few main points to be taken from my talk. First one is that, bless you. First thing is that now we have observations for 4 square degrees across 4 LSST deep drilling fields. So the observations are ongoing. With what we're planning, the ultimate goal is to build this unique legacy data set that combines this previously collected data with the new data that are coming continuously. And for each, the baseline at the end of time domes will be depending on the field, 15, 14 years. And then when LSST comes, it will build more, it will be a baseline of more than 20 years. So this is going to be quite a data set. Okay, stay tuned for new data releases. And I want to advertise a little bit that new catalogs of variability selected AGNs are coming soon, so please stay tuned. And this is the main point of my presentation. We are very much open for any kind of collaboration, for any kind of input, suggestion, help. So please contact us, and we will be happy to help. Maybe if you need something specific, maybe we can discuss it and maybe deliver. So yes, thank you very much.
So we have some time for questions.
Maybe an extension on what we were discussing this morning, whether there is already a plan to combine, maybe even in this calibration phase, some of the results from the DP1 with the data that has been already taken.
Yes.
So how can you use them for cross-calibrating or?
I mean, we can use them as the reference image, for example, for something like that. So yes, we are planning to do that probably next week. But there are a lot of things that have to happen next week, so I'm applying a little bit, but the plan is there. Yeah, definitely.
Any other questions? Yeah, I mean, I know we already talked about it, but I'm excited to see the live curves, and as soon as you have them,
Yes.
you want to put them on the size server.
Oh, yeah, right.
Yeah, there we go. See, I'm glad I mentioned it, and anyone else in the audience who's hearing that, you're like, right, okay. Oh, yeah.
I mean, so this is probably not something you want to take on, but just to ask, you know, that there are, of course, extensive imaging from, say, dark energy survey or from hypersonic prime cam also in these fields. That's probably the last thing you want to worry about right now. But you know, is there the prospect at some point of, you know, adding in all of those to build the most complete long-term light curves?
Well, probably. I'm not familiar with all of that you're mentioning, but probably yes. I mean, this is something that we should. I mean, if we are building the real legacy data set, we should include as many things as possible and preserve the information, right? Filling those gaps and everything.
I mean, yeah, there's a huge amount of data out there. You just picking strategically a few of the best ones that'll give you the most impact for your effort, you know, could be very valuable.
Thank you.
All right. Well, let's thank all the speakers again. I think it's coffee break time, so.
Is there GS data? Sorry. Is there GS data? Is that first?
Yeah, well, of course, they have their own.
Yeah.
Part of the field that includes several of those.
So the whole.
I haven't looked at even the exact field, but I didn't.
So he's gonna show you something on.
See, or?
Yeah.
Okay,
This is for a presentation of the data, 2009.
Okay, so let me see here. Waypoint for what's this on?
Everywhere.
Yeah, 2016, exactly, yeah, well, when I first got involved in 2014.
Yeah.
Okay, right, and it went about as good as any US project came, I mean.
Well, it's not just a US project, don't speed up the US.
No, the US is an amazing country again, right?
It's always been great.
We now actually. It's greater now.
It was always great, right? Unequivocally advised of using N words and anything we describe what it went. I'm actually impressed.
Yeah.
But it feels a little.
I remember,
Okay, well, yeah. Anyway, the point is, the US has always been great.
Yeah.
I've benefited from its greatness.
Yeah. Anyway,
Anyways, it's teasing you.
Yeah, no.
I know it's a set, no.
It went, but I mean,
You're my friend.
went about as well as any project could have, but, yeah, this is reality.
But I found it online. I got talk with ISO. I was trying to get ISO to, you know.
Get excited as well,
Yeah.
yeah.
It's all slides from, you know, the whole problem stuff.
Oh, yeah, I was more thinking, I can see myself.
All right.
Yeah. Right. Where does that fit into the picture? Is that a high?
It's very high, it's all the way up in the, it's really stuck on the top,
Okay.
way out to the surface.
Okay, so our first speaker of the session will be Scott Hagen, and he will tell us about AGN variability and feral nine. So please take it away.
Okay, thank you. So this talk is going to be a brief overview of my various attempts and thoughts on trying to understand AGN variability and what I currently think about AGN variability. And I'll apologize now if this comes across as a bit incoherent. You can blame my thesis, which will be submitted imminently. So, starting with the feral 9 light curves, this came out just shortly before I started my PhD. We have these nice, evenly sampled light curves from optical all the way to the X-ray over a decent amount of time. And what these allow us to do is really explore, okay, well, what's the physical conditions of the flow, because the timescales you see in these data depend on the physics of the flow. It tells us about the causal connection between different emitting structures, so you can see by comparing, let's say, the X-ray to the optical UV, that tells you something about the link between the disk and the UV color. But really what I'm interested in is understanding, okay, well, what's actually causing these light curves? And the place to start is reverberation. So we've had multiple people explain this already, so I'll keep this brief. If you believe standard Shakura-Sonnier disk theory, you do not expect to see optical UV variability on human timescales. The disk is much too dense, the viscous timescale is much too long, and so it should really just sit there and be more or less static. And so the way to get around that is by saying, well, actually, my X-rays do not come from the disk, because the disk in nature is much too cold. So instead, we have this low-density, geometrically thick plasma, and that can vary on really fast timescales. And so if you then say, okay, well, if my X-rays are varying, and my X-rays are more or less isotopic, some of these illuminate the disk, a fraction of which are absorbed by the disk, which then go into heating the disk, and that can drive the optical UV variability. The nice thing of reverberation is it's, I wouldn't say straightforward to model, but it's possible to model. And so that's what you're seeing here, where you've got a standard disk in black, and then in yellow, you have this brief X-ray flash propagating out across the disk. And as this propagates out to cooler and cooler regions of the disk, you can see how the SED is responding. And so we aren't just calculating time lags, we calculate the full time variable SED. And what this allows us to do is extract light curves in any given energy band and do point-by-point comparisons to the data. So give me an X-ray light curve, and I'll predict you what is the UV optical light curve. And that gives me something I can directly compare to the data. And so I built this model back in the first year of my PhD and put it up against the data. And generally what happens is it doesn't work. And not only does it not work, it fails for different reasons for different systems, just to make our life difficult. So if you see at the top here, you have feral 9, my favorite object. You'll notice the data in blue, and then the model is in red, and it's not even vaguely similar. 4151, however, you've got again the model in red, the data in blue, but you can see the way it fails is now, instead of completely under-predicting amount of variability, it has the variability amplitude more or less correct, but the timescales are all wrong. And if we think about, okay, well, why do we see these differences? Well, you can go to the SED, and the SED gives you part of an answer. So feral 9, you'll see you have this sort of fairly strong EUV component, so this is coming from your disk, and in comparison, moderately weak X-rays. And so what this means is that actually your X-rays are so weak compared to the optical UV that they just don't have enough power to make a significant impact for UV losses, and they're just being drowned out by your intrinsic continuum. 4151, however, has a similar amount of X-ray power to the optical UV, and so you're much better suited to make a substantial impact, and so you can actually drive a significant response. And so this, you could start interpreting in terms of, okay, let's say maybe these are slightly different accretion structures. And that brings me on to a very quick aside, in that AGN display quite strong diversity. When you go look at white populations, so here we use either zeta and perhaps the prime cam, and look at the SEDs, you see strongly different SED properties. And this is what Chris will talk about on Monday, what Claudio talked about earlier today. And these you can interpret in terms of different accretion states. And there is no reason to believe that these have the same variability properties. Physically, these are quite different. And so when we're talking about agent variability and modeling agent variability, we need to be clear with what accretion state do we mean. And so on that note, anything over here, I'm now going to ignore for the rest of this talk and focus instead on things that have a disk, because disks are much easier than ADAS. So, zooming now back to Feral 9, we know the revelation doesn't work, so the question I'm asking is, okay, what's actually going on? So here you have your X-rays in blue, your optical UV in green, the revelation model in magenta, and you looking at these light curves, you can start to get a hint at, oh, actually, maybe something interesting is happening here. So the X-rays are quite clearly dominated by fast variability. And if you take the autocorrelation function, so this is, think, a measure of similarity. If it's narrow, that means you're mainly dominated by fast timescales. If it's broad, mainly dominated by slow timescales. You'll notice narrow ACF. Your UV, which is quite clearly sort of slow, long-term trend, display smiley face, has a broad ACF, dominated by slow variability. The revelation, if predicts timescales almost identical to the X-ray. The smoothing you get from the light travel time is just not enough to match the timescales you see in the UV optical, even ignoring energetic arguments. And so what I think this is showing is that, well, actually, we need a second source of variability. And the obvious place to put that then is in the disk. And so we go back to the whiteboard and build a slightly more complicated model. So we start by saying, okay, we don't have Shakuras in our disk, hence why it is now green. So the color scheme here is outstanding and consistent. And so we say, okay, well, if it's not a Shakuras on your disk, then the Shakuras on your timescales go out the window. And so let's actually say that our disk is intrinsically variable on observable timescales. And so that gives us nice slow variability. But we still have this corona giving us the X-rays, and so that is still going to be varying, but fast on observable timescales. Then let's say, oh, this is an accreting system, so maybe these variations that we have in this start to propagate inwards. That's going to that means that your variability from the outer regions start to modulate the variability coming further in. On top of that, we do still expect to see a reverberation signal from the X-rays illuminating the disk. And then you can also say, oh, actually, my seed photons, photons that go into the corona and come and scattered up to the X-rays, these should originate from the disk, which if these are now variable, and that's going to introduce an additional source of variability into your X-rays. And so you have this nice feedback loop, which you can then put together, spend a few months writing your code, put it all together, and simulate a set of light curves. And what you end up with are light curves that, I should point out, these are simulated, that are qualitatively have similar properties to the data, in the sense that your X-rays are clearly fast, narrow ACF, your UV optical is nice and slow, and they also contain all of this information about how these different structures relate to each other. The only difference is now you put them in by hand, and so it gives you a nice test set to try and understand how the different techniques extract these. But this is just for the disk and the corona. We know AGN are a bit more complicated than that. We see things like the broadband region, we see things like winds, and so then you can ask the question, well, okay, well, how does this impact the variability? And the key here is that, well, actually, your disk is emitting in the extreme ultraviolet, and the extreme ultraviolet is optically fit to more or less anything. And so if you have some sort of material in your system, that's going to absorb a significant fraction of that emission. Now, a wind or the BLR, if you're an observer on the disk, is going to subtend a really significant solid angle. And so what happens is that you're now variable EUV emission. Some of it is being absorbed by large-scale material, and some of that is then going to be reprocessed and re-emitted as now variable diffuse free band continuum. And so you can ask, okay, well, how does that affect my variability? You do a bunch of cloudy simulations and swirl a bunch of cloudy, and then you end up with your nice SED with your additional free band continuum shown here in red. And it does affect the variability, but how it affects the variability depends on the energy band. So you'll see the light curves, the colored ones, this is including this wind, the black ones are the previous ones, are just a disk and a corona. And you notice the low energy light curves, so UV band, are much more strongly impacted than, let's say, UVW2. And this is entirely down to how much of a fraction your diffuse free band continuum contributes to your overall SED. You can then take this a step further and say, okay, well, in the revelation experiments, we like to measure time lags. What does this predict for the time lags? And you end up with saying, well, actually, most of what we see can sort of be explained just through reprocessing of this wind, where you naturally get this nice Panda jump. Because of the shape of the three-band continuum, you also have a nice fashion jump over here. But now the time lag isn't so much due to a different temperature gradient as you would normally expect. Instead, it's a constant time lag, but the strength of it comes down to the contribution of the diffuse three-band to the overall SED. I just want to point out, these data points, we didn't fit to them. This was our best guess, like this seems like a sensible place to put the wind. And so we made this model, and it seemed to work, and so I thought, yeah, great, publish, move on, and do something else. But models are never safe for very long, because recently, my collaborator Rick went and published the rest of the data. And so suddenly we went from about a year's worth here to a data set that suddenly tripled in size. And what usually happens when you triple your data set is it goes and breaks all your predictions. So we went and tried to actually test some of the things we thought we might see. Now, the first thing, once you stare at these light curves for long enough, and believe me, I have, you'll notice that, well, actually, there seems to be a slight dichotomy here in the sense that you've got this fairly low flux start and then a fairly sharp, strong rise before it then continues and for varies long as your typical stochastic variability. And so this doesn't necessarily look like a system that's just static. It doesn't look like, by eye at least, that your internal structure isn't changing. And so the thing to do is to go, okay, well, let's ask what is the SED doing? Because the SED, that's telling you about the energy generating structure. And when you do that, so we segment the light curve into bits and then calculate the SED. We did have more than just 2 band passes here, but it looks messy on the plot. And when you do that, what you see is actually, okay, well, between this low part and this sort of steep rise, you have a fairly significant change in the SED, but predominantly affecting your UV disk. You notice your integrated X-ray power does not really change. I mean, the photon index changes, but that's what you expect from the Compton balance. And so the easiest way to do this, so I mean, we're increasing the power, so you have to increase your m dot, but it's predominantly affecting the disk. And so one way you can do this, so you're saying, okay, well, my m dot is increasing, but I need it only to go to the disk. Well, let's just move our disk further in and say that actually there's some sort of structural change going on in the inner flow. Oh, okay. But that's all well and good. None of our models include this, I should point out. So, light curve modelers, we should start to think about how to do this. So that's all well and good. We think, okay, change is going on in the flow. But now what's going on the rest of the time? So if we look at the light curves again and just do a timing analysis, what does that tell us about the link between the disk and X-ray corona? And so we go to Fourier techniques. So this is a busy plot, I am aware. The top here, you have the phase lag as a function of Fourier frequency. So if you're not overly familiar with Fourier frequency, think in terms of time scale. So you're taking your light curve and you're dividing it up into many, many sinusoids, and you're saying, okay, my low frequency, that's my long time scale variability. My high frequency, that's my short time scale variability. The phase, that's saying what's the phase difference between my two light curves. So the main thing to know is if it's a positive number, that means your UV is coming first, followed by the X-ray. So negative number, your X-ray is coming first, followed by the UV. The bottom, you have coherence. So this is easy way to think about it is it's sort of like your correlation coefficient, but now split into frequency bits. Ignore anything in the gray region that's wildly biased due to interpolation scheme. But the thing to notice is you've got, okay, fairly low coherence actually throughout, which is not what you expect if you have propagations going into your corona, because then you expect actually most of this low frequency variability in X-ray to be driven by UV, so you'd expect higher coherence. You also have a really long negative lag, as in the X-rays go first, much longer than you expect from reverberation. That being said, that number is wildly uncertain because the coherence is low, so it could be anything. But the fun thing is, if you look at the red point, so this is when you then say, okay, what happens if you include a sort of fairly sharp rise where we're saying that this disk is moving inwards? Then suddenly your coherence goes up, so now your X-rays and disk really know about each other, and your lag flips. and I don't, how much time do I have left?
Another minute, it's okay, because we started a minute late.
Okay,
Right,
so I spent a long time staring at these, trying to think, okay, how can I actually try and model these and understand what's going on? Because my previous code is slow, it's not really meant for building data. So in a moment of despair, we went down and sat down and tried to write down an analytic model that you can just tweak the numbers up and see if you get something that goes through the data. So how does that work? Well, you start with an intrinsically variable disk and an intrinsically variable corona. So these have power spectra as such. At the moment, they're completely incoherent, so they know nothing about each other, so your average lag is 0, your coherence is 0. Then you say, okay, well, my seed photons to the X-rays come from the disk. So that's actually now giving you additional low frequency variability in the X-ray. It's giving you additional coherence in the at low frequency and the lag. Then you say, okay, well, my X-ray is now reverberating outwards. That's giving you now additional high frequency coherence and additional high frequency variability in the UV. And then because I think there should be a winter, I also put a winter. And the nice thing of this is if you pick your transfer function wisely, it's completely analytic, and so it's fast. And so you can make up something that goes through the data points. And so I'll summarize this very quickly. The key thing to take away from this, without going into too much detail, is that to reproduce these sort of low frequency coherences, because remember, we do need the X-rays to see some of the UV, because that's where the seed photons come from. So to reproduce this, you need the X-ray intrinsic coronal PSD to extend over a range of frequencies, so a range of time scales. And so what this is saying is, okay, well, you have a physically extended, radially extended corona, then you naturally expect a range of time scales, and you get this very flat PSD shape. And what happens in terms of the Fermi statistics is that we're actually then, because now you have overlapping time scales between UV and X-ray variability, that's giving you additional interference or uncorrelated interference, which reduces your overall coherence. To reproduce this rising part where the disk was moving inwards, you can still do that with a nice radially extended corona, but you really needed to see a lot more of UV variability and on much longer timescales than you expect from light travel time. And so this seems to be supporting this sort of very structural change going on. And so if I was going to start speculating wildly, I would say that my current thoughts on what variability in Ferrel 9 is doing is that, okay, well, most of the time when if your structure is not changing that much, then you're reasonably stochastic and your X-rays and UV disk only really know about each other weakly through either seed photons coming from the disk and some reverberation moving outwards. However, if you have these nice structural changes where, let's say, m dot increases, that would naturally go from the outwards and in because that's where your material is coming from. It's an accreting system. And so that, if that leads to now more significant changes in your inner regions, then that's your X-rays need to respond to that. And so that gives you additional coherence. But then that needs to stop at some point, and so you just return back to this nice stochastic variability. And so I think I'm out of time now, so I'm going to leave you with my summary slides. Yeah, thank you.
Thank you. One or two quick questions, perhaps? Who's first? I saw you first.
In terms of the acidity, you have the UV and the X that comes from the central part of the object. These objects are big on the sky. So when you say that you're using other photometric points, they are coming from the entire host.
No, so these are just Swift points. So we have the U-Mot.
Okay.
So the U-Mot has 6 filters on it, and then, so we have a few filters in the UV optical, and then you have the rest of the X-ray band.
Yeah, but the optical has a much more than the nuclear component.
You take out those galaxies.
Yeah.
So you take off, so that is the.
Yeah.
Okay, you didn't mention, I would like to understand if you were focusing on the center. Okay.
Have you tried any kind of recurrence analysis?
No.
The student analyzing Claudio's 1ES object, and it strikes me that this would be a really interesting subject to apply to.
That would, yes, we should talk more about that, I think.
Okay, very good. Yeah.
So this doesn't sound at all like a deaf random walk. I mean, is it? Is that a demonstration system that's not a deaf random walk? I mean,
well, I mean, I don't. Starting to be too controversial, but I don't necessarily think HMR just count random walks.
That shouldn't be controversial.
Yeah. Because they're not, I mean, if you look at the PSD for downtown walks, it's sort of like the platinum and one brick, right? Whereas if you think about stochastic variability, and if you especially have these propagating fluctuations, your variability is increasing as you're going further in. So I expect at least one more brick in there. Yeah. Just if I'm waving my hand a bit, and then yeah, I think it's probably more complicated than the book.
All right, I think we'll move on to the next speaker. Did you come up? Okay, so our next speaker is Daniel Roberts, and he will tell us about self-consistently modeling massive black hole growth within Decode. So please, take away.
Thank you. So yeah, I'm Dan. I'm a PhD student at the University of Southampton, working with Francesco Shankar, and I'm going to give you a brief overview of Decode, which is our semi-empirical model that our group works on, and I'll give you kind of a brief summary of the simplified version that we've input into Agile to assign the black hole that's in there. So I need to tell you as we're at an aging event, but in our understanding, every local massive galaxy hosts a supermassive black hole. And LSST is going to observe billions of galaxies and tens of millions of AGN across a vast area of the sky. And so it's a good time to start collating kind of a package of theoretical models that can add context to observations and provide kind of theoretical expectations to compare against. And one of those we're looking for in terms of the tomography and the black hole galaxy connection is Decode. So the black holes at the center of these galaxies display tight correlations with a number of host galaxies properties, including stellar mass, as displayed on the left, and the stellar velocity dispersion displayed on the right. And these tight correlations have been interpreted frequently as evidence for a degree of co-evolution between the black holes and the galaxies. And theoretical models have been able to reproduce these scaling relations, at least locally, invoking mechanisms such as AGN feedback, supernova feedback, and mergers. But the degree of this coevolution is highly dependent on the mechanisms you include, and not only the mechanisms you include, but the implementation of these mechanisms. So while most of them it predicts some degree of coevolution, the exact extent is still debatable. But in terms of the observational side of things, there was this nice paper from Salvato earlier this year who showed that up to redshift of 4, there seems to be no real significant evolution in the stellar mass black hole mass relation. However, as soon as you go above this, the observations from LSST and previous quasar surveys suggest that things start to become increasingly more overmassive. At least for the quasars, this could perhaps be explained by Eddington bias, as you're intrinsically looking at the brightest objects, and so you're going to pick out the most overmassive ones. And what we're expecting is that as GEMINI approaches lower luminosity AGN, you'd expect to find these sitting slightly closer to the local relation. However, we found that those displayed here from Harikane and Maialino are actually still as overmassive as the previous ones, being with ratios of kind of 10%. And it's unclear as to whether these are truly representative of the underlying population, or whether these are just the most overmassive objects in the tail of the distribution. However, with time, it is appearing that, so here's a plot from Svegers' work, that when you do stacking, you do find that we are finding more low luminosity AGN that are close to the local relation. So it seems that it's possible that these overmassive objects are just a tail distribution, and that you would expect that the scatter in these relations decreases with redshift as you invoke mergers and AGN feedback tightening these relations. However, it's still unclear exactly where these sit and the implications for the black hole galaxy connection and the black hole tomography cosmic time. And so at this point, most people would usually turn to theoretical models. And so these can be broadly categorized into 3 types. You have your cosmological hydrodynamic simulations, which actually trace the dynamics that are closest to real physics. However, they're computationally expensive, and they still rely on semi-analytic prescriptions for the subgrid modeling. You have the semi-analytic models, which are faster than the hydrodynamic ones, still trying to follow the underlying physics, but they require significant tuning. So, for example, Gaia tunes on the stellar mass function up to redshift 3. And so from redshift 3 to redshift 0, the prediction of stellar mass function isn't a true prediction because it's being tuned to it. And then you get semi-empirical models. they're kind of have come on quite a lot in the past sort of 10 years or so. They're fast and flexible. They're data-driven models with minimal assumptions, but it's not necessarily easy to see the underlying physics that's going on. It requires a bit of legwork to try and gain insights into quite what is exactly happening. So I'm going to focus on the backhaul side of this because of the type of the event. But we have Decode. This is a very fast semi-empirical model. We start from dark matter merger trees, and then we grow galaxies within these via the star formation rate halo accretion rates relation, inputting kind of quenching recipes to quench the galaxies, and then we grow black holes according to the observed specific accretion rate distribution function, and includes merger trees, the dark matter merger trees, convert these to black hole merger trees, incorporating the merging timescale of both the galaxy and the delay for the black hole coalescence. And this is taken from a parameterization tuned on specific hydrodynamic simulations. And from this, we can then integrate this across cosmic time, look at the growth of the black holes and the black hole mass function, and then obtain things like both galaxy and black hole statistics, their relations and related quantities. So, due to this kind of uncertainty over the initial conditions, I'm going to briefly do a little comparison between two models. So we've got a kind of fiducial model where we see via the local relation. So this solid blue line here, the rate of voluntary relation, and it's grown via the observed distribution function of accretion rates, and then an LRD-like model. So we're seeing these black holes significantly overmassive along this blue dash line, and they're grown by a boosted accretion rate distribution, such that when you convolve with the stellar mass function, you obtain the luminosity function of the little red dots. And then from this, we can compare the two and look at how this might impact the evolution through cosmic time. So here on the left, you've got the fiducial model, and on the right, you've got the LRD-like model. And this is displaying the black hole mass function, redshift 5 through to redshift 0. And so you can see that despite the fact that the initial conditions in this orange sort of histogram are over an order of magnitude and a half apart, the local relation, which is the uppermost histogram, are almost identical, only showing a slight difference in the flaring at the very high mass ends. However, the most obvious difference is that while in the fiducial model you see this typical significant redshift evolution as you'd expect from a typical continuity equation model, in the LRD-like model, you see a very suppressed evolution up until redshift 3, until realistically the specific black hole accretion rates that these are being assigned become significant. You can then compare the mean black hole mass stellar mass relations. And so again, on the left, you've got the fiducial model, and on the right, you've got the LRD-like model. And in the fiducial model, we see that you have very little evolution with time, and this is backed up by what would be expected from some observations, at least at redshift below 4, and also is consistent with previous theoretical models. And in the LRD-like model, we see this rapid evolution down towards the local relation. And this is because the motion within the stellar mass black hole mass plane is dictated by the ratio of the specific black hole accretion rates to the specific star formation rates. And in this model, because you'll see that it's such an initially high normalization relation, this ratio is very low. You see this motion towards the local plane. And because we believe that from residuals analysis, that actually the black hole mass velocity dispersion relation is the most fundamental relation, it's important to also look at this to see if we can reproduce this. So here we're assigning the velocity dispersions by tracing the sizes of the galaxies through cosmic time, and assigning them via the genes modeling of Chris Marsden from 2022. And so we see that in the fiducial model, we see relatively weak evolution with time, but in the LRD-like model, we're consistent with the local relation throughout the entire epoch, from redshift 5 to redshift 0, which is something that matches the observations, where we find that despite these objects being significantly overmassive in the black hole mass stellar mass plane, they seem to lie along the black hole mass velocity dispersion plane. I think these results need to take with a little bit of pinch of salt. We're still kind of working out a couple of things out and how we track the size of these galaxies, but I don't expect the results to change kind of significantly. And of course, we can also then look at the motion within the planes. In particular, when it comes to the importance of quenching is whether or not these galaxies are approaching the mean relation from above or below the relation primarily. And we see that in both models, we expect that these galaxies actually just grow along the relation. There's, apart from initially where we see this kind of rapid decline towards converging towards the local relation, once they reach there, they seem to just grow along it. So there doesn't seem to be anything to suggest that you would expect them to primarily come from cosmic noon above or below this relation. And so yeah, so that's kind of the black hole side of things primarily, but we're also doing a lot of stuff on the galaxy side. So one of the things we're trying to do is investigate the quench fraction. And so we've currently got 4 empirically based quenching recipes implemented. On the right here is plot from Hamilton of the local quench fraction compared to some observed ones. And for 2 quenching methods, we've got the halo quenching, which is following the halo shock heating, so the approach of Deckel and Bernborn from 2007. And then we've got the black hole quenching, which is an assumption that the black hole mass velocity dispersion relation is driven by AGM feedback. And so when you surpass this relation, you get this kicking in of AGM feedback. So it's a very simple kind of empirical way to do this. We are currently working on kind of a more robust way where we effectively curve the star formation rate of galaxies via the AGM light curve. So yeah, so just to summarize kind of a few of the things that we can predict. So we can predict the halo galaxy connection, galaxy statistics, black hole statistics, black hole galaxy scaling relations, the scatter of these and trends within the scatter, contribution of accretion and mergers, things like this. And what we're working on doing is things like AGM clustering, environmental effects, and then we're doing a more detailed treatment of the merging timescale to then try and make predictions of the gravitational wave backgrounds. And then just to finish off, just a brief bit on kind of simplified version that we put into Agile. So we start off by only tracing the means here. And by only tracing the means, we have three parameters. We have your choice of stellar mass function and your relative and kinetic efficiencies, and those population average, so they're slightly easier to make reasonable guesses about. So we take statistically generated dark matter merger trees. We create average halo growth tracks. We then assign average stellar growth tracks by the stellar mass halo mass relation, as obtained from abundance matching. And then from the observed specific accretion rate distribution, we then assign a mean black hole accretion rate, and self-consistently includes the mergers via the merger tree. And from this, we can produce the mean black hole growth tracks, and from this, also the galaxy black hole galaxy scaling relations. And so on the left here, you can see the black hole mass stellar mass relation, which is used in Agile to assign the black hole masses. And on the right is just this these black hole mass stellar mass relations convolved with the stellar mass function to obtain an inferred black hole mass function. And I haven't shown it here, but Aga has already tested it in Agile, and we can reproduce the Anana active black hole mass function at, I think it's redshift 0.15 to 0.3. And we can also reproduce the active black hole mass function of Schulze at slightly higher redshift. So yeah, I'll kind of leave it there with some takeaway messages. So if you want to kind of put across the decodes in a fast and flexible way, you can quickly explore parameter space. So for instance, here I was running something, the box size is about the same size as TNG 300s. It took about 15 minutes to run, and this is just on my little laptop. But as soon as we kind of get all the recipes kind of sorted out, the aim is to kind of parallelize this, optimize it for distributed memory, run on HPC, and we should be able to get up to very large volumes very quickly. In terms of the impact of the initial conditions, we see that the fiducial model has a black hole mass that evolves significantly with time, and stellar mass black hole mass relation that doesn't, whereas the LLD-like model has a black hole mass function that evolves weakly with time, and a black hole mass stellar mass relation that evolves significantly. Yeah, I'll leave it there. Thank you. Questions? Yeah,
I wonder, do you ever look at luminosity or star formation rate versus the luminosity from AGN, which again, a long time ago when I was looking at it was very discriminatory much more discriminatory than some of these relations mass, which are very difficult to measure. Luminosity is easy.
Yes, so to all our galaxies, we have assigned a star formation rate that's taken from the UV. So you can convert this into a luminosity if you wanted to. At the moment, we haven't looked into this specifically, but I think it is something that we should look into.
Maybe we can talk.
Yeah.
Another question here?
Yeah.
In your thought of the black hole mass over time, having approaches, some of them started at like 10 to the 8. How do they seed those ones?
So we're just seeding along the stellar mass black hole mass relations at redshift 5 in this, and then evolving it downwards. As this is to look at kind of what the impact is on black hole galaxy connection, the black hole demography, from whether or not these high redshift AGN are representative of the underlying population, or whether you're just looking at the tail of the distribution, right? So we're limited in terms of our redshift range by the observations that we put into this, because we're putting in observed distribution functions of the derivative quantities to get the integrated quantities. But we're working kind of an extrapolation, so that when we put a simplified model into Euclid flagship as well, we can then run it up to far higher redshift. That's what we're aiming for.
Yeah, Gordon. So, sorry. Yeah.
Model. Do your conclusions about the black hole mass, galaxy stellar mass relation, and the relative role of accretion versus mergers basically come out in agreement with what we derived in the Jana? Yes. Are they quite a bit different?
No, so they agree. So we can find a variation in the contribution of mergers depending on how you deal with the timescale, and you start to make it how you assign the black hole accretion rates, which kind of can dictate the scatter a little bit. And so if you increase the scatter, you get slightly higher contribution mergers. But no, they're generally consistent. And we've done this for using the Fanchao distribution, the Bongiorno distribution, one from Yang, and a couple of others. And we find that the results are pretty much consistent. The real difference is kind of the redshift and the mass limitations of those distributions.
Okay. And so, we ended up quite skeptical about the black hole growth model used in illustrious TNG.
Yes.
It seemed like they're almost trying to hit the local observed relation instead of the debiased relation.
Yes.
Do you have the same type of conclusion? Or you?
Yes, so for illustrious TNG, they are tuned against the Coleman-Ho relation, right? So this is the relation for dynamically measured elliptical galaxies. So that is going to be intrinsically higher because the black hole mass stellar mass relation is significantly dependent on the morphology of the galaxy.
Yeah, okay. Yeah, so
I was going to ask just about that. Have you considered adding in galaxy type into this at all? Because
yes,
some evidence that, at least for the inactive population, the black hole mass stellar mass relation depends on galaxy type.
Yes, so we are currently tracing so not only the galaxy size but also the Boltzmann ratio. So we're aiming to do some morphology classification off of that. We're still kind of cleaning some things up in exactly how well we can reproduce the size mass relation at high redshift.
Great. Fantastic. All right. If no further questions, then we'll thank the speaker again. All right, so our next speaker is Matthew Brandt, who will tell us about ZTF, of course.
Well, I'll think a little bit about it.
Okay.
So for those who don't know, my name is Matthew Graham, and I'm one of the PIs and the project scientist for ZTF. So if you have any ZTF complaints, talk to the other PI. If you have some question, happy to talk to me. As Jelko said many years ago, LSST is really just ZTF 2.0. So there's a lot of stuff that's being developed. ZTF, just to give you a recap in case you don't know, 47 square degree field of view camera with 660 million pixels. Up until a few months ago, it was the best camera in the world. But Palomar is probably still the best site for time domain astronomy because we have a robotic telescope at the 60-inch with an IFU on it, which does a lot of the supernova spectroscopic follow-up for ZTF. And we have the 200-inch, which has a brand new spectroscope on it. which is going to be great. So ZTF can do 4,000 square degrees roughly in an hour down to about 21st magnitude with 30-second exposures. And we have a robotic filter arm which allows us to do G, R, and I at the moment. And we've been going now for 7 years. In terms of data volume and stuff like that, we are a 10% LSST. So that's why we've been helped to do a lot of development. In terms of numbers, we've actually covered twice the LSST 10-year total in sky coverage. So that's one area where Rubin's never going to beat us. We're almost at 1 trillion photometric measurements now for about 5 billion sources in total. But for 2 billion of those, we've got up to about 1,750 observations in G and R from -30 up. Now that's great because Rubin goes to +30, so there's going to be a nice 60-degree area of overlap. We do about 1 million alerts per night, and we've put over 800 million alerts out in the last 7 years, and that's about 70 terabytes, 65 terabytes of data. So if you want all of those, we can send us some disks and we'll give them to you. But in terms of where we've been thinking, so currently our current funding from NSF is for this year and next year, specifically to do overlap with the first year of LSST. We hope we've got our money for next year, but of course, with the current state of NSF, we don't know. So we can promise that we're going to go through to July of next year with the partnership funding if the NSF goes away, but if the NSF is there, we should be good until the end of next year, and then we don't know about 27 onwards. We've generated, as I said, about 800 million alerts to date. Only 500,000 of those have ever passed a filter in one of the brokers or in our internal systems to say it's interesting. So that tells you that, 1 in 1,000 alerts is actually going to be interesting to someone. So forget about 10 million alerts or 40 million alerts. It's 10,000 or 40,000 a night. Only 5% of the AGN that we know in the ZTF dataset have ever produced an alert at that 5 sigma difference. So again, the discussions about what you're going to get out of alert streams is a very small fraction of what AGN are doing. Now, they're probably the most interesting AGN in some ways, the most active, but be aware that it's going to be the annual time, the annual data releases, which are going to give you much more information about the AGN population. Our pre-LSST, this is the current data setup we have internally in ZTF. So ZTF goes into this piece of software or infrastructure we call Kowalski, which then goes to Fritz, which is our open source Marshall, which is what we use to handle the 50 or the 500,000 alerts. Essentially, this receives the alerts from ZTF. It does spatial cross-matching against archival catalogs. There's a full light curve in there for each object, and you can also put the spectra and all the other things you can gather from there. You can use Fritz to trigger automatic follow-up and other telescopes and all that sort of thing. It runs machine learning models on the alerts. We have this thing called BTS bot, which is a full end-to-end automation from the 48-inch using the 60-inch to do automatic spectra reduction. And so we've got, I think it's about 100 type 1a supernova now in TNS. And the record is an hour from detection with ZTF through to it being reported to TNS, fully automated machine learning classification and data being taken to the 60-inch. And there was not an ATEL, a note that went out earlier this week that we got with BTS bot nearby. We got a swift observation 6 minutes after its detection with ZTF, again with these automated systems. So in terms of follow-up, I think there's a whole point about having these automated systems. You don't want humans in the loop, just automate the whole thing and you'll do much better in terms of responsivity for the past stuff. User-defined filters and sending filter. Now we're redesigning the LSST because we can cope with 1 million alerts per night on a single machine at the moment, but 10 million is a little bit more, and so we need to do something. This constant cross-matching has turned out to be a real problem, and how we write our filters at the moment is not user-friendly. I'll talk about that a bit in a minute. We're using Rust-based code now. We've switched to Rust-based code with this new thing called Boom, which is replacing Kowalski. better parallelization, lower latency, modularity distributed, all those sort of things. And it's going to be feeding two things. It's going to be feeding Sky Portal instances, which is what our Fritz stuff does, and it's going to be feeding Babel, which is our Rubin broker. What can we do? Yes, so we've tested that we can run at scale. So we can handle ZTF and Rubin coming in together. What's going to happen is that every new ZTF alert will be matched with what we know about it from LSST, and then there will be a dedicated stream from Babel where you'll be able to see this is the ZTF alert that's been cross-matched against Rubin. And the reason for doing that is we've tried it with some DECAM alerts coming through. So this was the first ZTF alert, but then you can use the fainter telescope, the bigger telescope, to get the pre-detection stuff and see what's actually going on. And then that helps with your classification. So if we're running classification from the ZTF perspective, substitute LSST in here, and that will help with the classification for what this is, and we'll do much better then in increasing the purity of our rare things that people want to do automated follow-up on and things like that. Most brokers filtering, yes, so most brokers offer this sort of, you write a static filter, there's some limited filtering from a web app, or they run user-provided Python filtering code. Problem is we found, I mean, we use a system underneath and it has a very complex non-Python syntax for doing that, and our users hate it. And they want to be sharing filters, or we want for efficiency to pre-compute blocks. So on the brokering side, we've redeveloped, so it's a sort of really old, funky looking click and drag and click thing where I can just write things in terms of rules, and then we'll pre-process some of those for computation. And with Babel, what we're doing is we're aiming to offer a number of phenomenological filters to say sort of, is this alert brighter? Is this alert bluer? Which are actually the things people seem to be most interested in when they're doing selection, rather than more sophisticated, is this a type 1A? They've got their own models downstream that they can handle at the rates when you filtered it down. But the initial filters, people wanted to go, I just want to know if something is brighter or bluer or something like that. We've definitely seen. We will support a number of community driven, and we're still trying to figure out the details of that precisely. And the synergy is already happening since beginning of June. We've actually been covering the prospective SV area each night in GRNI. That's using our public time. So the alerts from those are already coming out. So when the SV data comes out next March or April, you'll be able to go back and see what ZTF alerts came out during this period when it was observing, and fill in the gaps and see what was doing stuff. And consequently, you'll see the thing that went off in September, look in the SV data rather, for the precursor stuff and see what's going on. But AGN are slow transients, and they're much more interesting because a lot of the stuff we've been talking about is sort of fast stuff. So there's a lot of phenomenology that we're seeing in the AGN area, and we can attempt to organize that in some better way. But I think most of these, I should have done this as a bingo card, most of these have been mentioned sometime this week. So what are we doing in ZTF help? Well, at the start of this year, Shimon Naknoshny, who's my former postdoc, we put out the first version of the ZTF AGN catalog. This is the 5 million that we've been talking about. Interestingly, we've only done it for 790 million objects in ZTF so far. The next version will be more, but one of the things we have found is that and look in it's on archive, so look in there for details, but one of the things we did find was that the efficiency in terms of classification is dependent on cadence and baseline. And there are some graphs in there which tell you, if you want this sort of accuracy and this sort of baseline, this is what the F score is going to be and that sort of thing. So there is some interesting thoughts to be had about where we want to be with the first, given our initial 300-day baseline, how good can we get? And where will we be after year 2, year 3, year 4, year 5? Which I think this is very relevant for defining. More interestingly, most of you should maybe have heard about Scary Barbie. This is the thing that was reported 2 years ago as the biggest bang. It peaks at minus 25.5, 25.6 in absolute magnitude. It's at redshift 1. The the spectra seems to be, maybe it used to be an AGN, or maybe it was never an AGN, but now it's an AGN, but there is a wise echo, there's a wise echo, but no prior wise data rather. And the explanation for this is that it's a very large TDE. So I think actually they've downplayed the mass now somewhere between 3 and 10. And so obviously we went looking for this was initial ZTF discovery anyhow. It's called Barbie because of this silly ZTF name that we have. It looks like an anagram of Barbie. This is Jason Hinkle's plot. These are these ENTs, is extreme nuclear transients, and the top one of those is Scary Barbie. So I wrote a paper in 2017 where I described things called massive AGN flares, and so if you see where those lie, so there are obviously a lot more ENTs out there. So there's obviously a population of AGN which have got TDEs going on in them, is the idea, and these are probably more massive stars. And then we looked back and we found this thing, which seems to be even bigger than his data. So we initially called this just Ken. Actually, we initially called it Psycho Ken, and then we realized that Psycho is probably a trigger word, so we went with just Ken. And then for other reasons, we changed it to Superman because we're in 2025 now. This is the red thing. It's at redshift 2.5. It's emitted about 10 to the 54 ergs of energy so far, which is a solar mass. It's got absorption outflows. It was definitely an AGN before. And when you try and figure out the TDE mass that can give that sort of energies, it's probably at least 100 solar masses in terms of the star that's being shredded. So there is probably a population about there. More interesting, another one of these interesting ENTs is this thing. Maybe it's periodic in some sense. So that's the ZTF data, but I think we've been hearing a lot how, 10 years is not enough, you need these 20-year baselines. So when you go back and look at the 20 years worth of data, this is what it actually is. So this is flux. So this went off in 2003, and you'll notice that it dips below where it was before, and then there are a couple of pikes, and then just as ZTF was starting, it came back and now sort of burbling along, which it wasn't doing previously. So again, we think this is another one of these TDEs where there is an existing AGN, so there's an accretion disk, so there's interesting interactions going on there. There is a stellar population in the disk, and I think we're seeing a lot of the most interesting flares, the strongest flares are coming from all sorts of things. We do expect a top-heavy IMF in the disk, and there is some notion of these immortal stars, which are these 1 to 200 ones, so maybe that's what we're seeing with Superman. Maybe it's the one I've seen, we're sort of seeing stuff which is probably further out. But these have to be interacting, and whether they're crossing or whether they're being threaded or whatever, we're sort of seeing things, I think, the most extreme ones. Also, the interesting thing is you can have both prograde and retrograde, and if you have a retrograde one, then you should see after the initial spike that it goes down below. So what we think, our interpretation for this is actually this is a partial retrograde TDE. In an existing AGN at about a redshift of 0.4. There's a lot of other interesting stuff about this one, but you'll see these, both this one and Superman on archive in the next few months. So there's a lot of interesting things, but you need the 20 years of data here because that's the really important thing for adding in. So one of the projects that we're working on now is we're doing force photometry of initially all Pan stars positions in ZTF, which gives us force photometry down to about 22nd magnitude. But if we use the ZTF catalog, the catalog itself, we can actually go to about 24th magnitude. And so there's a new thing we're about to start, which will do that. So we'll have ZTF photometry, force photometry, science image, it's detrended, so the calibration is much better, the photometric errors are less for about 3 billion sources. And we're waiting to hear whether we've got funding for that or not at the moment. But this is certainly happening now. And people are looking this for periodicity detections, but there's a lot of AGN obviously just sitting in there that we're interested in finding. I'll do a quick plug for UVEX. If you have any influence, please get NASA to launch UVEX because it is such a wonderful complement to LSST, and it gives you the UV stuff that you need, which is really good for AGN. And finally, we're in Durham. So this is some thoughts that the Venerable B put down. about this sort of thing, and so here's your English translation. Bay heat, what long enduring, what Thomas reveals in the heavens. So wonderful, it's amazing what you can get ChatGPT to do. Rubin Observatory Concord LSST should extend its work through 20 years. Bede was right. And weave each night spark into the chronicle, firm enough for posterity that dim mass of unseen kings be weighed without deceit, and their concord be plainly set before the learned. So I think that's it very well. So, there you go. Thank you.
Yeah, very nice. I have two questions. The first one is concerning the beginning. You were mentioning this very fast as with follow-ups.
Yes.
Can you say where Southeast work for you?
Yes, so BTS, so we have these automated systems, and I think they have a program of TOO times that they can call on Swift, I believe. And so I think it's just automated triggering and dropping it in, and they're getting a really quick response that way. So
it's very quick.
Yeah, it is. I know it's ridiculously quick, but the thing is that the detection is, the alert comes in, all that, the machine learning has been very fine-tuned to try and get it as quickly as possible, because these are people, they're interested in looking at F-bots and infant supernovae as well, where they need to get onto it as quickly as possible. So we have, lag times trying to minute down. Now, I think Rubin's going to be better because Rubin has 120-second lag time to get the alerts out. And then the hope is to get onto those things quickly if you're interested in that sort of thing.
Yeah. Yeah. And the other question instead concerning the second part of your talk, these weird objects.
Yeah.
So if they are TDE, you manage to do a TDE with such a massive black hole, just because because the tidal radius is going to be it's going to make it a bit complicated. So they are maximally spinning, or is this
no. So the masses are 10. So for Superman, the mass is 10 to the 8.4, but it turns out because the star itself is so massive, it doesn't necessarily need to be spinning. You're still in the area where actually alpha could be 0. It could be slightly curved, but it doesn't need to be. So I think that's the saving grace of if you have the very massive things, stars. With the other one, the retrograde one, the mass there I think is maybe 3 or 4 solar masses. It seems to be, but the mass of the supermassive black hole for that is 7.8, 7.7. So that's not the problem. But I think with the massive ones, it doesn't necessarily need to be most spinning. And I think that's what they found with Scary Barbie as well.
Questions?
Very short one. When is the catalog of the ZF AGN going to be released?
Yeah, so
I'm waiting for it.
Yeah, I know. So there are several. I mean, like Rubin, there are several catalogs, right? So Shimon's paper he's just revising the final reviewer's comments. Some of that requires a little bit of revision of the catalog. So once that's accepted properly, that will be out. So that hopefully is in the next month or so. And then we need to think about what we're going to do with the 2.0, where we do the inference on everything, and then there's the catalogs of the forced photometry AGN, which are being identified. And so there's a body of catalogs that I think could be coming out, and we've got to figure out what's going to happen with those and what's it. But the initial 1.0 of QZO should be hopefully in the next month or two, just assuming we can, that these are the final comments of the final regiments that the referee is happy with.
There's a question online from Swire.
Oh, sure. Go ahead.
Hi, Matthew. Thanks a lot for the talk, and lovely to see all those names popping up. I just wanted to have a question related to what Mara was asking from the ZTF AGN catalog. What's the possible false probability rate going in that case? Like, how many of these can be really candidates if we follow up a few more years, or baseline might not be ended up being an AGN?
As AGN, well, so it's an ensemble catalog which uses variability and also currently WISE data and stuff like that. So, and the cutoff, the public catalog, the catalog that will be released is a probability of greater than 90% of being an AGN. and that's 4.8 million. There is a parent catalog, which is just everything that sort of passed, and you could make your own cuts on that, and that's 55 million. And we may try and find somewhere to put that so people can down select and whatever. But I think, as I said, I think we've done about 20% of the possible things we can infer on, but some of those have less number of data points at the moment, but they may have enough to put them in, because we're running against everything we detected up to January 24. We now have another 18 months data that we could put in and rerun and stuff like that. So at some point we will run out and there will be a final, but I think we're maybe thinking now about having a couple of successive versions as we go forward and retrain and things like that as we go forward.
Thanks a lot, Matthew. Just later on, we would be very happy to hear from you more about Babamul, because we are really looking forward to putting our watch list over there as well and trying to learn a little bit more about that.
Yeah, well, we'll see how it goes with it.
All right, let's make Matthew again.
A minor comment that ChatGPT might well make that brothers and sisters.
I know, but it's B.
I know.
Yeah, and I know Darrow was a double monastery.
I think it consists of history or stuff, positive.
Okay, our next speaker, Ashraf, will tell us about scaling relations of the dusty torus in the BLR. Please.
Hello everyone, I am Ashraf Aydinian from Seoul National University. I am happy to share my recent work regarding AGN variability titled Scaling Relation of Dusty Torus with Luminosity and Broadline Region. This work has been done in collaboration with Professor Junhoi Gu and Drs. Shubang, Amit Kumar Mandal, and Lunghun Sun. As we know, AGN's brightness can fluctuate significantly over a wide range of time scale from just a few hours to several decades. In general, the fast variability is associated to compact and small regions. For example, fluctuation and instability in accretion, this can produce rapid variability. Over the longer time scales, the variability can be related to extended regions, for example, the dusty torus. So based on these properties, AGN variability is a very powerful tool to establish and to probe the nature and structure near the structure of regions near supermassive black holes. Over the different wavelengths of AGN variability, the infrared variability is associated to hot dust. As we know, the dust grains in AGNs can receive UV and optical emission, and we process it in infrared wavelengths. In type 1 AGNs, it's believed that the near infrared emission belong to dust grains in near part of torus. These dust grains have a temperature near to sublimation temperature. Among the initial attempts, Barbins in 1987 for first time tried to estimate the size of torus. In general, in this type, the size of torus means that the radius of the inner part of torus. So based on this equation, the size of inner part of torus is scaled with AGN luminosity with a power of 0.5. The early near-infrared reverberation mapping established a tight correlation between the size of torus and luminosity, and they reported that this correlation is agreement with sublimation physics, and also this conclusion is in agreement with interferometry observations of torus. But the number of agents with available near infrared reverberation mapping data is very limited. So in recent years, many studies moved to in mid-infrared voice data to establish the correlation between the size of torus and luminosity. However, these studies reported that the size-luminosity relations is shallower than 0.5 as predicted by theoretical studies. Regarding these conclusions, we have to consider that if this relation can be the result of a sample selection effect or other physical mechanisms are responsible for producing such relation that is shallower than theoretical predictions. To answer this question, in this work, we try to study the size-luminosity relation more carefully. So in this work, we selected 150 unique agents with uniform H-beta light measurements. And also we included 32 high accurating agents from SAM, Seoul National University AGN monitoring project. Since the second goal of this work is comparing the size of torus and the size of broadline region, we selected agents with reliable H-beta light measurements. And we collected optical data for this sample from ground-based surveys, and we also considered the mid-infrared light curves from voice. In comparison with previous studies, our work offers some improvement. For example, the light curves has been used in this work has a longer baseline. We collected all photometric data until about late of 2024. And also our sample has a uniform analysis of H-beta light measurements. And also we included high accurating agents from SAM project. So it helped us to constrain the high luminosity end of size luminosity relation. And also in this work, we corrected mid-infrared light curves for accretion disk contamination. Here is example of our analysis. As the primary method, we use ICCF to measure the lag, but measure lag from ICCF is not necessarily reliable. So we selected targets that there is a very strong correlation between optical and mid-infrared light curves by employing our max value more than 0.6. And also we evaluate the likelihood that this observed correlation may produce by chance. So we rejected all objects that this likelihood is more than 1%. And at the end, we visually check the quality of lag measurements. So after this quality assessment, we have 92 agents with reliable lag measurements. Then we check the size luminosity relation in both W1 and W2 bands. And in this figure, the red points are high accuracy agents from SAM, and the blue shows the targets from literature. And the green shows the relation. So as we can see, both in W1 and W2, the size luminosity relation is steeper than is shallower than 0.5, and the slope is in order of 0.35. So we also, to obtain this relation over a wide range of luminosity and dust size, we combine our sample with our previous work. I have to mention that in both study we employed similar methodology, so we don't expect any this combination sample produce any bias. So after combining the samples, still we observed that the correlation still is shallower than 0.5. Before we consider this finding as the final conclusion, we have to be sure that our sample and our results is not biased with luminosity. For example, at first we have to be sure that the sample with no major lag are not clustered in low luminosity. So to check this factor, we selected all variable agents in our sample with F bar more than 5%. And then we compared the distribution of luminosity between two samples. And we have done some statistical tests, and we found that there is no significant difference in luminosity distribution between AGNs with reliable light measurements and AGNs with no light measurements. So it suggests that our sample is not biased to low luminosity. And also, as another check, for AGNs with no light measurement, we have done Monte Carlo simulations, and we for a range of input light measurements, we obtain the probability of light detection, just to be sure that for AGNs with no light measurements, if over the wide range of input lag, probability is low or high. So as we can see here, for most of targets, we found that the probability over the wide range of input lag is small. So in general, these findings suggest that our sample and our conclusion is not biased by low luminosity and also by time sampling of voice. However, in some cases, for example, as we can see in this figure, we can see that in a small lag, the probability is not negligible. So so based on this finding, we cannot rule out the effects of voice sampling on our results. But we don't expect a significant effect. So if our result is not affected by sample selection, some physical mechanism should be able to explain why this correlation is shallower than 0.5. First of all, I have to say that these scenarios, there is no strong and enough observational evidence for these scenarios, but theoretically, it seems that these scenarios can explain. For example, the first scenario is anisotropic illumination from accretion disk. According to this scenario, the radiation from accretion disk toward the poles is more stronger in comparison with equatorial direction. And also, some studies suggest that the bright and luminous AGNs have thinner torus. It means that the fraction of geometrical thick in comparison with radius is small. So the combination of these effects suggests that in luminous AGNs, the major lag is smaller than we expect, and it can produce a shallower slope. And the second scenario is that the dust grains don't reply to a change in accretion disk to accretion disk very fast. So it takes time to these dust grains to adjust themselves. And also the third scenario is that self-shadowing effect can result in a shallower slope. According to this scenario, due to the structure of a slim accretion disk, the dust grains in inner part of torus reduce less radiation. So we measure the lag smaller than we expect. And the last scenario is that the theoretical models assumed a fixed spectral shape for all luminance. But the fact is that the shape of SED is dependent to luminosity, and the amount of radiation that dust grains can receive depends on the shape of SED. We don't know how this factor exactly produce a shallower slope, but this is the factor that we have to consider when we discuss the slope of relation. And also, based on Broadline region reverberation mapping studies, previous studies suggest that high Eddington ratio AGS deviate from the size luminosity relation. Based on these findings, we were motivated to check this matter for dust. So we divided our sample to low Eddington ratio, intermediate Eddington ratio, and high Eddington ratio. And we checked how these AGNs deviate from size luminosity relation. However, we couldn't find a very strong relations, but we found that, for example, in highest bin of Eddington ratio, the majority of targets has a smaller dust size than we expect. That again, it can be explained using the self-shadowing effect. And in addition to gas luminosity relation, we compared the Broadline region and torus size, and we found that in general, the torus is about 10 times in W1 and 14 times in W2 larger than Broadline region. And also we found that the relation between these two regions is slightly steeper than linear relation. We expect that using the spherics data, we could solve the measurement of small lags in low luminosity and of relations, and using this data, we will be able to constrain this size luminosity relation much better than exciting voice data. And also using the LSST data, we would be able to determine this variability for a very large sample of agents, and this is something we plan to do in our group in future. So here is the summary of my talk, and thanks so much for this.
Questions?
Can you split the relationship up? So you do it only for AGN, you think of as around 10% of Eddington, and then do it again for AGN at Eddington's, or?
You mean deviation from?
Yes.
Okay. So
is it clear that this that it goes with Eddington ratio? So is it the changing SED? You're talking about self-shielding rather than the SED itself changing.
Yeah. In self-shadowing effect, actually based on the structure of accretion disk in high Eddington ratio, we expect that a fraction of this radiation cannot escape from the accretion disk, and they cannot escape. So the dust grains receive the less emission from accretion disk. So
does the BLR. So the BLR is also slightly shielded.
Yeah,
so
yeah,
they
yeah.
go together.
Yeah,
And
exactly.
is this so? It's consistent with what you see that the two of them go together, but not as you might expect.
Yeah, we expect a similar effect both in Broward region and tourists together.
Yeah.
Yes.
Yeah, very nice, thanks. So we know that for many objects from interferometric studies, a large fraction of the infrared flux comes from the polar region, right? So is this something like that could help you, I guess, like if you have material farther away?
Yeah, actually, in this work, we didn't consider the emission from polar, and we assume that all infrared emission comes from equatorial torus.
And may I comment on this? May I comment?
Yeah.
Okay, so from polar, we mean that radiation is dominated in M ion, which is more than 8 micrometer or 10 micrometer. So these are actually NIR. Vice versa are actually NIR. These are 3.4 micrometer and 4.6 micrometer. And they are dominated by equatorial and radiation temperature.
Okay, but you expect a gradient temperature even in polar dust, right? So in principle, you would dust there. And this is something that in principle you can already kind of simulate using like results.
Yeah, actually, but for simulation also we just considered the infrared emission from equatorial torus, and in general we didn't consider the polar. Yeah. But yeah.
A question?
Yeah, but the selection you had at the beginning requiring a strong correlation between W1 and optical, you had some, does that select a certain geometry? Is that a bias? Does he throw away all this that don't work, that don't fit in the picture? Is that possible? So maybe I got it wrong. You only looked at systems where there was a strong correlation coefficient between W1 and optical. Is that one of your conditions?
Yeah, to select more reliable light measurements, we just considered when the optical and infrared light curves are strongly correlated. And also that previous studies considered these are max value about 0.5 or 0.4. But in this work, we considered 0.6. So we rejected many targets, but we preferred to have less targets, but more reliable measurements.
But is that not a correlation due to bad data, bad sampling, or the geometry of the system is different and there is no correlation for those guys?
Maybe, but just we don't have information about the geometry of our all agents. Just we know that they are Taiwan agents, and we don't have more information. But maybe
Are there some systems with good optical and good infrared data where there is not a good correlation, where you can prove there is no, like, there's just no correlation, so the dust is not where in the same place as it is, like they were talking about? Is that true? Are there some systems with a different dust geometry?
Yes, I
think so.
Yeah.
I think we should continue the discussion afterwards. So thank the speaker again. And I think Swaram is online.
Yes, I'm over here. Thanks.
Please, whenever you're ready.
Sure. Thanks a lot, Colin. Just to confirm, can you hear me well and see my screen? Yeah, I can see that. Okay, yeah. Great. Thanks a lot, everyone. I'm probably the only one sitting between your dinner plans and for the next day. So my name is Swam from the Panda. I'm a science fellow currently at GEMINI Observatory in La Serena. And today I'm going to sort of partly give a talk on behalf of my wonderful colleague, Igor Benatti, which is about exploring quasar variability, where we are trying to explore this universal relation with Eddington ratio, and also going to sneak peek onto things that I'm really interested in working on, changing looks, and finally, a new supermassive black hole scaling relation, not just any other, but maybe something very interesting for all of you. So starting off this work, this was briefly mentioned in yesterday's talk in by Luis, when he's basically considering the double peak AGNs. So this basis of this work starts with Igor's work, where we are, thanks to the collaboration with Mike Iraklis, we are sort of collecting this ARCMIS sample, which is the all-quasar multi-epoch spectroscopy. This is part of the Black Hole Mapper project of the SDSS-5. So effectively, it's going to take into account 22,000 quasars on the whole sample. This is basically divided into 3 bits, the ARCMIS wide field, about 22,000, and the medium field, about 2,000, and there are the specific reverberation map field, about 1,000 of them. So for the one in the medium field, we are focusing right now on the medium field here. This is marked in the red in the polar regions here. And this is effectively going to be scanned 4 times during the survey duration. So out of that, we ended up having 2058 type 1 quasars spanning the redshift range from 0 to 3. Now, this is basically trying to show and highlight how the ZTF, I'm not going to talk a lot about ZTF, Matthew gave a fantastic talk on that already. So this is basically the overlap of the GRI bands on the different spectra that we have been collecting from the different redshift range, spanning from a very local case from 0.25 up to redshift 2.5 and higher even. So effectively, we can characterize different parts of the spectrum, sometimes getting estimates of the BLR emission lags, and effectively sometimes just being able to do also continuum reverberation mapping to infer the accretion sizes, accretion disk sizes. So effectively, with this sample in mind, we did a cross match with the existing SDSS DR16 quasar catalog to infer the spectroscopic properties that has already been compiled in Wen-Chen. So effectively getting the black hole masses, volumetric luminosities, and specific line properties such as the O3 5007 properties. Effectively, what we ended up doing is now we have this big sample of about 915. So we ended up looking at the ZTF light curves of them. At that point, when we started this work, this was the 6-year-long ZTF light curves, and trying to do a sort of a automatic process to remove outliers and infer the variability statistics using the fractional variability F-bar metric. So once we do that, we are kind of showing here the pipeline and how the algorithm works. So effectively, we are only sampling those where the light curve length gives us more than 100 observations in G and R band effectively. And if not, then we are discarding those bands and effectively keeping only those objects where the fractional variability is above 0. So effectively, this is one exemplary case of this object SDSS, where we can clearly see the 3 bands, really good connections, and the outliers have been removed out of the 4 sigma threshold. So G and R pretty much very well known, but I band a bit more sparsely sampled here. So what's really after the point that also Luis mentioned in his talk, that why we are taking the G band as our reference here, effectively in the major sample, we effectively see that all of the quasars, they have the G band metric, and 911 out of the 915 have the R band. And here's the correlation between, histograms showing how well the 2 of them behave. So effectively, that was our criteria, taking the G band as the basis for all of the correlations that I'm going to show you later. So effectively, all of these light curves now are all processed, and the paper is out in APJ. And thanks to Igor, we have been able to ingest into the SAI server, part of which Amy is being leading the efforts, which will be part of the data challenge. So looking forward to that. And effectively, the biggest result that came out of this, after all correlations that we managed to do with the black hole masses, with the effective properties on the spectral lines, what we've found out is the most robust anti-correlation is actually between the Eddington ratio and this variability metric FR. So this here in this plot is showing the sample divided in bins of redshift. And effectively, we can really appreciate the strong anti-correlation that's born out of this. The problem with the double peak, effectively, which was a big question yesterday, was the measurements of black hole masses, which are dependent on the full width half maximum, are still intrinsically assuming Gaussian properties for these double peak, instead of the one where we should actually be looking for accretion disk model fitting, of this naked disk profile fitting, and recovering the remnant part, which could be the core of the disk, the BLR emission. And effectively, that goes into play as the virial mass indicator. So a work has been initiated. Now, Luis and together, we are trying to re-infer these black hole masses for the double peak AGNs and trying to reestablish those effects that we are also seeing with the generic type 1 AGNs over here. So effectively, this is a very interesting correlation that Luis was able to now infer black hole masses independently from the full width half maximum, but by using the variability metric going forward with the Rubin data in principle. Now, since we are on the topic of Eddington ratios, I just wanted to also highlight things that we have been working for a couple of years with Jana. This is basically sort of a very heavy work that we managed to do in the last couple of 3 years, taking into account all those well-known AGNs that have been already satisfied by up to the Sloan Digital Sky Survey's DR4, or the fourth campaign itself. So there are more than 100 changing look AGNs effectively having multi-epoch spectroscopy with SDSS, which had already been categorized as changing look or changing state AGNs. And again, basically trying to make Chris happy and effectively what Claudia has been doing. But we also figured out that we were one of the first to actually figure this out from this homogeneous reanalysis of the spectroscopy. And we're working on the light curves right now, so stay tuned for the paper too. Effectively, not talking more about the other parts, but really trying to highlight again that indeed the peak of the distribution for these changing look states, effectively in their dimmer state, is really peaking at 0.01, which is really characteristically similar to what others have been finding. More recently, there is a much bigger database coming out from the DESI survey, the DR1 release. So Wei Zhan and collaborators, we have been looking at that. And now at the point, we have 561 changing look AGNs from DESI and repeat spectroscopy from past STSS campaigns. And also they are able to recover the median Eddington ratio around 0.01 from this DESI sample. What's interesting with this increase in number counts, we're actually seeing a much more similar ratio of the number of turn-offs and turn-ons effectively in DESI. So effectively, when we end up going to these larger sample sizes, we are actually able to encounter more of a similar nature or fraction between the turn-offs and turn-offs in that. The big takeaway message from this work was that we were interested in actually tracking the movement of changing look AGNs on the so-called quasar main sequence. So the quasar main sequence is very interesting from the point of view that the two axes, which actually in the optical plane is the full width half maximum of H beta, and on the x-axis is the strength of the Fe2 emission in the optical. They are neatly correlated observationally with the black hole mass and the Eddington ratio. So effectively, any such movement of the changing look helps us to understand the changing state nature or transition between population A to population B type, and effectively whatever intrinsic changes happens to this emission line with respect to the changing continuum. A very interesting point was raised in Mara's comment in two questions to Claudio's first slide, which was basically, are we seeing this kind of nature of change effectively when the continuum goes down, we're still seeing the signatures of the emission line. And that's a very interesting problem that we are trying to tackle as well. We have been trying to compile a long set of data for this very well-known candidate, NGC 5548, traversing around 43 years of light curve data, spectroscopically speaking. So we ended up really reevaluating all of these spectra to recover their H beta light curves, all from spectroscopy, and the corresponding continuum 5100 angstrom from the same spectrum. So what we are noticing is that when we are effectively looking at this very well-known sampled AGN, and we are able to recover the time lags effectively for different campaigns independently, and when we do perform the delagging of the H beta with respect to continuum, we are able to recover a very neat correlation, which is the well-known Pronek-Chuvayev effect from the early 1970s. So it is effectively telling us with the increase of the incident continuum, the H beta or the BLR's response is effectively going to get saturated at a point where you can really recover this as a broken power law, that after a certain luminosity state, the H beta is not responding because the Strongian sphere has basically been ionized effectively. And this is very interesting, and follow-up work is coming along where we are inferring the BLR properties as a function of changing state and changing SED properties for this very interesting AGN. So effectively, this is very interesting because NGC 5548 also lies pretty much at that threshold of log Eddington ratio -2. Now, coming on to a very interesting part, which probably also is very relevant to LSST, is basically what are the timescales? Matthew mentioned this very much in his talk that 10 years probably is not enough. And this is something that has been probably been realized over the period of time before the start of the instrument. So H beta reverberation mapping typically takes about 100 to a few hundred days, even for the most luminous AGNs, the local AGNs that we're talking about. But while we are going to the high redshift cases, the C4-based reverberation mapping is the sort of the way to go. And it takes off the order of a decade to 2 decades of monitoring. And this has been a painstaking work taken care of by Shai Kaspi and his collaborators back in 2021, where they monitored and revealed the radius luminosity relation for carbon-4 for 38 AGNs, spanning a very wide range of redshift, and also a very well-known wide range of luminosities. So effectively, the question is, if we are going to do the same strategic point of view with LSST, effectively, we are not going to get most of these AGNs at all, and forgetting about the radius luminosity relationship that we can construct for these very high redshift AGNs. So we need to change a bit of our strategy while looking at these cases. And effectively, what we ended up doing with Francisco Pozo-Nunez together is that we do have these spectra available, and also a lot of these were taken from the Southern Hemisphere, thanks to Paulina Lina and her collaborators. So we are now trying to establish how we can optimize certain instruments, meter class instruments, which are fitted with medium to narrow band filters, and effectively isolate the regions which are just not being contaminated by emission lines or diffuse continuum emission. I really like the talk of Scott, where he mentioned a little bit about the diffuse continuum emission. And effectively, this is one way going forward where we could try to isolate the pure continuum emission that's coming from the AGN. This is a very nice example of that. So in lieu of that, we are sort of building out, we built a model, effectively now coming back to the standard accretion disk as our foundation stone here. And we are now trying to convolve a transfer function of effectively all of these filters to the X-ray driving light curve, which is basically drawn out of a Timmer-Gorkonic algorithm with a power spectral density where alpha is -2. Not only that, we are trying to introduce as many contaminations that we could really anticipate in lieu of the LSST light curves. So effectively, contamination on different ranges of BLR emission coming from the SDSS distribution of spectral parameters, and scattering such as the diffuse continuum. So there is a sort of a database of diffuse continuum emission generated using physical properties of these SDSS quasars, accounting for differences in the host galaxies and nuclear extinctions altogether. And this is now neatly tied up in a modular code, which is also going to be a part of the data challenge, creating Mott light curves for going forward with the testing of the LSST cadence. And effectively, we are able to now constrain and train this model and trying to recover the accretion disk time lags and corroborate against the C4-based reverberation lags that were measured. So now for the big reveal, effectively what we are able to find out, now whatever you see in the yellow dots are basically the theoretical expectations that we're getting, where the y-axis is the carbon-4-based reverberation lags coming from Shai-Kaspi's results, and the respected x-axis, corresponding x-axis, is the accretion disk closest to the carbon-4 part using these pairs of light curve that we are trying to optimize using these meter class telescopes. And we also have observation results from two of our very good candidates from the Southern Hemisphere. These are part of Paulina's sample, CT286 and CT406. Effectively, these are the actual accretion disk lags that we have been measuring about that. And the plot, if there's a takeaway from this plot, is that the carbon-4 emitting region, the reverberating region, is a factor 165, 66 times larger than the size of the accretion disk region. So what that really turns out into is that we can, if we do measure the accretion disk sizes, we are at more efficiently and effectively sampling the accretion disk, where we can scale to get the BLR radius and effectively measure the black hole masses for all the number of AGNs that are going to be observed in the future. Now, to give a context how fast and how efficient this method is, I have a very small table over here. So effectively, if you're talking about a BLR lag of about a year, so about 360 days, multiplying to the Nyquist frequency, the lag of the accretion disk can be measured of the order of 4 days. Now, if you go on the sampling, going up to the cases where Shai-Kaspi was actually looking into, which takes about 16 years, about 6,000 days, it will take off the order of 2 months effectively to get those characterization of the accretion disk, estimate, recover the BLR lags, and effectively measure the black hole masses for these cases. So it's a very rewarding prospect to actually make use of these ground-based meter class facilities, where installing effectively these optimized filters can really help us avoid a lot of questions that we are having with the cases of contamination scattering, which is of course very interesting. And that's where we are also using a lot of these our modular models in order to incorporate these contamination to create Mott light curves for these LSST AGNs. And finally, this is something my good friend Rodolfo mentioned in his talk, where he gave a very nice overview of Scorpio. So this is something very interesting we are coming along with. And I wanted to mention something about the Open Sky program that is available to each and every one of you if you're interested in asking for observing time with Gemini facilities. So effectively, what that really means is that we have this coverage and all these slew of instruments that we are really building up, and it ensures that any qualified scientist, regardless of affiliation, is able to access these facilities and ask for time with this infrastructure under the Astronomical Event Observatory Network, or AON. So effectively, this is going to be a very nice channel where if once we get a trigger from one of these brokers, or effectively by any other resources, you can really trigger this under our GOAT system. And if this can really be minimizing the time it takes to process the application, request for a disruptive rapid TOO, and effectively get your data very, very fast. And just wanted to summarize the talk by really telling you all about how many ways you can request for Gemini time on these facilities. So as many as the days of week, effectively, pardoning the Saturday and Sundays. So you have the regular programs, which is once per semester. This is upcoming in September, the next one. Then you have the large and long programs where you can request for time for up to 6 semesters, so of the order of 3 years. And then we have the fast turnaround, which Rodolfo briefly mentioned. This happens every month. Effectively, if you have a very nice changing effect or a very interesting candidate that you want to follow up, that of course you're not waiting until the semester end. You could really process that, and the projects and the proposals are evaluated on the go within a matter of 3 to 4 weeks. These are inserted in the pipeline, and they would be observed in the next 3 months. This is the mainstay of the observing time. Then, of course, you have the DDD time, where you can be requesting at any moment, and effectively this takes of the order of a week to be evaluated, even less actually. It'll be evaluated within a couple of days, and your observing target is in the pipeline to be observed. And also, not to forget the poor weather proposals, which effectively, if you're looking at very bright sources, can also be something of interest for the community. So effectively, not taking more of your time. If you want to learn more about this and the other facilities that we're going to talk about, please join us for tomorrow's breakout session, which is about watch lists and follow-up from the LSST alert stream. And if you have any more questions about Gemini or any other things, here's my email, and I'll be happy to take questions.
Thank you. Questions in the room or on Zoom? There's one question on Zoom.
Hi. I guess it's me, right?
Yes, go ahead.
Yes. Thanks. Very nice talk. Among the many things that you touched, the relation of the variability with the Eddington ratio. I think that's you're finding something that it's in part known, although then there are other parameters underlying this relation. So there is the mass as well, the luminosity we have to really understand. But even more interesting probably is to try to understand how this depends on the time scale that you're sampling, because this way we understand how the power spectrum is evolving with all these different parameters. I always fear that when you present it in this very compact 2D form, you're hiding a lot of things underneath what it's really
Absolutely.
happening.
Yeah, I agree to that point. And I think this is something that we are working currently to effectively check for longer baselines and what really happens if we account only for the cases where we have actually more number of observing visits, like more than 300. And what we are seeing is that the scatter in this relation starts getting much, constrained. But effectively, yes, you're absolutely right that all of these correlations are basically born out of the luminosity and mass relation, because that's basically what's happening in the Eddington ratio. The part of the power spectra, this has been handled by another student of Thaisa, and effectively, I hope in the next meeting we will be able to show some of these results in sort of agreement to what Patricia Arevalo and her collaborators were looking for in this sort of uniform power spectral density for AGNs that they're finding as a function of accretion rate really is not varying much over the restricted redshift range they were probing. But yeah, something to work on as well. But thanks a lot, Marisa.
So follow up on Maurizio's point. Chelsea McLeod did a nice two-dimensional diagram of basically F bar versus mass and luminosity, and in a 2D plot, it's really I think a lot clearer to separate out the mass and the luminosity. But I wanted to ask about the changing look AGN. So in your paper in 24, you show and in fact you had it on the screen, the mass versus Eddington ratio, that as we're doing this transition, as the broadband continuum spectrum is changing, by using the standard single epoch masses, we get the masses wrong. It's clear the mass of the AGN has not changed, but when we look at it through the lens of scaling relationships, we get things wrong. And I'm worried about that for your carbon-4 variability disk size. They're working when things are scaling, but what happens when they don't scale? Did you
Very interesting.
That relationship?
Thanks a lot, Chris. I think I really was anticipating a question like that. So I really agree to the point that effectively the black hole mass hasn't changed, but effectively the way we are estimating using the virial relation using the single epoch really is the characteristic behind this movement of the objects on the black hole mass Eddington ratio movement. What's really is more useful is probably looking at much more direct parameters observables like the full width half maximum and the parameters like FE2 in intensities. And from the past cloudy simulation that I've been working around for about half a decade now, we really understand it on a better way that there are characteristic differences in the accretion disk as well as the BLR properties that effectively give rise to these correlations with the RFE or the FE2 strength and the Eddington ratio. Now, coming to the questions of carbon-4 lags, the interesting bit is that we do have dedicated monitoring using photometry, which we are doing on almost like intra-night basis. But effectively, we're also getting the spectroscopy on a regular basis. And by the usage of these very medium band filters, we're talking about less than 100 angstroms there, we're trying to avoid these cases. But of course, I think it's a very good thing to try also look and investigate on these cases where the Balmer jump and effectively those higher order helium ionizing front, effectively really blue words of the carbon-4 is going to show up and very much more intensely than if like we have it for NGC 5548 or other cases. That's something on that is going on. I think I'm very interested in building up this kind of database, looking into DESI as well. And if there are any characteristic cases where we effectively can sort of separate out these samples of those where the scattering effect is more dominant and those where effectively it's more like a typical AGN where effectively when we see a star-forming galaxy where these bumps are much more prominent, are getting washed out. So a lot of work to be done, but yeah, very interested in that direction.
Okay, I think we're going to get kicked out of the room very soon. So thank you, Swayam, and let's thank all the speakers.